or truly anything that, well, that binds and substitutes variables. So of course, the goal of this talk is to hopefully convince you by the end of it that if you are to implement one of these, you might want to consider our library. But I'd nonetheless like to take a bit of time at the start to explore the idea behind the library. So this is exactly what I'm gonna do, and we're gonna see what's the idea. So for this part, we're gonna use everyone's favorite programming language, the Lambda calculus, and here you can see a Haskell representation of its abstract syntax. And already here we have a really important question to answer. How are we gonna represent variables? So the choice made by Rebound, and hence the choice we'll make as well now, is to use de Bruijn indices. Hence, we're gonna use natural numbers, but already there we have an opportunity for improvement if we use dependent Haskell. What we can do here is index our whole representation of terms by a natural number, which is going to act as an upper bound on the number of free variables in the term. To get this idea to work, we use this fin n type instead of the nat type, which represents natural numbers, yes, but only the ones which are smaller than the index of the type. This representation might seem familiar to some of you, and actually you might have seen it maybe in the Bird and Patterson functional Perl from this very same Haskell symposium, albeit a few decades back, in the Bound library, which is based on this same paper, or finally in a number of Agda papers which use similarly indexed representations. So this representation here is fine, but before we move on, I'd like to do a tiny change to it. You might have noticed that in the abstraction case, because an abstraction is binding an extra variable, we need to increase the bound on the number of variables in the body of the abstraction. And what I'm gonna do here is factor this increase into its own type. Doesn't really change anything to the representation, but having a separate type will be really useful later on, so keep that in mind. So now we have a representation. So we can use it to implement something, and what we're gonna do now is an evaluator for the Lambda calculus. As any good interpreter, it's going to take two arguments. One is going to be an environment mapping every variable in scope to its value, and one is going to be a term that we are in the process of reducing to a value. The type of environments is going to be left abstract. The main thing we need to know about them is that we can look up any variable using this kind of bang operator and get a value out of the environment. The last thing I need to define now is our values, and because this is a pure Lambda calculus, we have only one kind of values, abstractions. And I like all of my values to be closed, so rather than saying that the body of the abstraction can contain any number of free variables, I'm going to use the bind zero type, meaning that there are no free variables in it. And here you can already see the benefit of indexing all of our types by a natural number. We have this extra type safety. As I said, we can force values to be closed. And in my evaluator, I can enforce that my environment maps every variable in my term to some value. Now onto the actual implementation. So the case for variables is easy. We just look up a variable in the context and return that. For abstractions, it might be tempting to say, oh, I just got an abstraction. That's already a value. I can just return it. But here, pay attention that the type of my eval function tells me that there can be free variables in my abstraction, and of them to be specific, and values should be closed. So of course, here what we could do is implement another function which is going to walk through the body and replace every variable by its value. But we can be smarter than that. What we can do instead is change our type of values, not to be plain closed abstractions as before, but to be open abstractions with a closing substitution, promoting them into closures. And this way, in my abstraction case, I just have to pack the current environment with the abstraction and return the whole thing without doing any more work. Finally, in the application case, we just have to evaluate both operands recursively, scrutinize the left-hand side, which is going to be one of these closures, unpack the environment, and if we extend this environment with a new binding for the bound variable that we're in the process of replacing by the right-hand side, we can just evaluate the body, And with that, we have a perfectly functional interpreter for the Lambda calculus. So as I said, it's perfectly fine, but I have two issues with it. The first one, it only works with open terms, closed terms, sorry. It might not seem like it because my signature is taking a term with n free variables, but whenever I have such a thing, I have a closing substitution very close, so we do not really allow open terms. Second issue I have is that it doesn't really look like the Lambda calculus, or at least it doesn't look like a research paper on the Lambda calculus. If you read a paper on this topic, and more specifically about big step semantics for the Lambda calculus, you'll find a rule like this, and you can inspect it as much as you'd like. You won't find any mention of an environment or a closing substitution in there. Which means that if you were to try to implement this, you'd have to put this extra effort and risk introducing bugs. So instead, we're going to try another approach. We are going to try to re-implement our evaluator, but this time following this rule to the letter and do nothing else. Hence, the signature doesn't take an environment anymore. It takes an open term and returns an open term, also solving my other issue. For variables and abstractions, there is nothing to be done. No reduction can occur. However, when we have an application, we just follow the rule. We evaluate both operands. We scrutinize the left-hand side, which is going to be an abstraction. And here, we do the reduction into steps. First, we use this instantiate function, which corresponds to the substitution. And then we reduce the whole thing. Of course, now I need to implement this instantiate function. There are multiple ways to do that. We're going to use one device known as parallel substitutions, which take every variable in the scope and replace it by a term in another scope. So these parallel substitutions are going to be represented using this env type, which is suspiciously similar to the environment from our first implementation. And with this device, how can we implement instantiate? Instantiate should replace the first variable, the bound one, by the argument and leave all of the others untouched. So we create a parallel substitution which does just that using this, can I point here? Yes, I can. This combination operator to replace the first variable by the argument and leave all of the others untouched, acting as the identity. So of course now I need to implement the substitution function, but this one is easy. Whenever we have a variable, we just replace it by whatever is in the environment. When we have an application, we apply it recursively. And in the final case for the abstraction, it is slightly more complicated, but not much. All we have to do is shift the environment around, as one does with de Bruijn indices, and apply this new shifted environment to the body of the abstraction.
What is IDs?
IDs is a parallel substitution which acts as the identity, not replacing any of the variables. Does that sound good to you?
So it's a type N or something?
It is of type env NN. It maps every variable to itself. So now we have another implementation, which again is working just fine, but we've introduced another issue here. Namely, to do this reduction, we now have to walk the body of the abstraction twice. Once to do the instantiation, and once to actually reduce the things we got from the instantiation. And as you can guess, walking through the term twice is inefficient. So is there a way to make this implementation more efficient? Well, more than that, I'd like it to be more efficient in a sneaky way. What do I mean by that? Well, this is the code we have for the evaluation. And as I said, it solved all of the issues I had at the start with the first implementation. So I'd rather not change this code. Of course, performance is not going to improve magically. So if we don't want to change that, well, we do need to change the other piece of code we had. And here, we can reuse the same trick we used in the first implementation. There, whenever we had one of these abstractions, rather than walking through the body and applying the substitution, what we did is that we packed them together and returned the whole thing. And we can pull the same trick. Oops. In my bind type, I will add a substitution, a delayed substitution, which means that in my subbind function, rather than taking the substitution and applying it outright as we did before, we can now instead take it and stash it in this brand new field we've added in our bind type. because we might have already stashed another substitution there, we actually have to fuse the two of them using this funny operator, but no actual work is getting done. And it's only in the instantiation function where I have to walk through the body of the binder anyway to replace the binder by the value we're instantiating it with, that I will do all of these substitutions I've fused together and the instantiation all at once. So, and as you can guess, doing this fusion is more efficient. So, of course, up to this point, I've been kind of hand-waving about performance, what seems more efficient, but we can benchmark this. So we're going to benchmark our 3 implementations. Of course, we need a benchmark, and we're going to use this big term known as Lennard's term. Fundamentally, it's doing a lot of natural arithmetic using church numerals, so as you can guess, many beta reductions are going to happen. The first implementation of the interpreter is really fast, 0.2 milliseconds. However, our second implementation with the substitutions is super slow, 3 whole seconds. The silver lining, though, here is that just by delaying substitution at the level of binders, as we've done in the last version, we're back to 0.7 milliseconds. So this is still slower than the first implementation, but we're getting all of the benefits, and we're in the same ballpark. And this is my first takeaway from this talk, namely that if you are to implement something based on these naive substitutions, delaying them at the level of binders can improve performance dramatically. So up to this point, I've been talking about an implementation of the lambda calculus, but a good implementation doesn't make for a great library. So the first question I want to answer now is, can we actually turn this idea into an actual library that you and I can reuse for other things? The second question is, well, if you were to use a library to handle variable binding, you might expect a bit more from it than just binding variables one by one. So does Rebound offer a few more features? So regarding my first question, this is all of the code we've written for the last implementation this far. And the game is going to be to see whether we can factor it into client code on the left for you and library code on the right. So here, all we have to do is first, we're going to fault eval because it's taking a bit too much space. Then we can turn this subst function, whose implementation is very specific to the lambda calculus, into a type class, moving the implementation to the side of the user. And the last thing we have to do is change the library so that it can work for any type of terms, not only the lambda calculus, but here we just have to abstract over this type. And we're already done. And here, I'd like to take a minute to contemplate what we have. On the right, we have this library code, which handles variable binding and uses these delayed substitutions for performance. On the left, however, we have this implementation of the lambda calculus, which crucially did not change from the first implementation based on substitutions we had. And what that means is that it does not know about delayed substitution, nor does it need to know. And this is a key design choice of Rebound, namely, the main APIs of the library do not expose delayed substitutions to the users. We do still offer some lower level APIs because manipulating a delayed substitution explicitly can be useful at times, but these are not the main APIs of the library, which completely abstract delayed substitutions away. So now let's talk about some additional features. If you were to implement something a bit more complicated than the lambda calculus, let's say the lambda calculus with pairs, you might want to bind things which are a bit more complex. As an example, up right here in the object language, we have this binder where it is binding 3 variables at once, and more than that, it's binding them according to a nested patterns of pairs. So Rebound allows you to easily implement that in your syntax. All you have to do is first declare a data type to represent your patterns. So in our case, we have 2 different kinds of patterns, single variables and pairs of sub-patterns. The type is once again indexed by a natural number, but this time this number is here to track the number of bound variables by the pattern, meaning that the variable case is a pattern of 1 because it binds 1 single variable, and a pair of patterns has to bind as many variables as the sum of its two sub-patterns. Then, in your abstract syntax, you can use this slightly more complex form of the bind type, which takes a whole pattern, and meaning that you're binding the whole pattern all at once. And this way, Haskell's type system is going to be able to statically tell you that whenever you're working in this term T2 on the right, you have m plus n variables, the m being bound by the pattern, and the n variables which are free in the overall term.
Is pat the same as pattern?
Did I? Yes, I did mess up. I forgot to rename all of my occurrences. Thank you for pointing that out. This should be pattern as well. My apologies. So, sorry, what?
What's the if there?
Sorry, I did not get that.
ICFP after bind.
This is the type we're binding in. So we're binding an expression. So, oh yes, I see what's the issue here.
The XP is unbound.
Oh, that's a very good catch. I made two mistakes here. Oh, rather I made two mistakes. I named pat instead of pattern, and x should be tm. My deepest apologies for this scarfuffles.
TM of n or TM of n?
The n is right, yes. So here, this kind of patterns is enough to support arbitrary data types and pattern matching in your object language. And those of you who are familiar with dependent Haskell might be wondering about how hard does it get to program when you have these type-level operators such as plus involved. And our answer to that is yes, internally, and by internally I mean in the library, things can get a bit hairy or complex to get right, but it's more than manageable, and this complexity doesn't really leak to the users. So we think this is fine. If you're interested in more details, please check the paper. So another thing is that the Brown indices are great internally to bind variables, but they make for terrible surface syntax. I think that all of us will agree that writing code like the snippet on the left doesn't sound pleasant. And worse than that, if you are to ask your users to write code this way, and they make a tiny mistake and you spit back this error message here, I don't think they're gonna stay your users for very long. So here what you should be doing is that you should allow your users to use source level names, let's say string, map them to the Brown indices, and whenever you want to speak back to your users with error messages, you should translate back. Here, I assume some people are going to scream reader monad, and you would be right. The only issue is that if you really want to leverage all of the type information we have, the reader monad is not going to cut it, because you're going to run into issues due to the indices we have in all our types. That being said, Rebound offers a slightly more general version of the reader monad, which is also indexed, and this allows you to get all of this implemented very easily. So now I've talked about Rebound the library, but there is one last question about it. Is it actually any good in practice? And I want to explore two different questions here. The first one is whether it's expressive enough. Can you implement interesting calculi using Rebound? And the second one is performance. In the very first part, I've showed you that the IDs seem to be efficient. Is it actually in practice when you start implementing more things? So regarding the first question, we've implemented many different calculi using Rebound. The list is on the left. And the, let's call them features, used by one or more of these calculi are listed on the right. And of course, all of these examples are self-contained, documented, and available on our GitHub repository. I just want to quickly highlight one of these features on the right. It's going to be the very last one. People here who have implemented substitutions before know that this subst function we had to implement before can be a bit repetitive to implement. And Rebound actually can derive this implementation for you if you use something called generic programming. So, as a bigger case study, we've also re-implemented PyForall. That is a dependently typed language which is used to teach people about dependent types. And a few features of this language include dependent data types, which means again, for the people knowledgeable about dependent types, that rebound needs to support telescopes, and it does. It also has dependent pattern matching. And finally, it uses source level names, which means that it puts the reader mode that I've mentioned before to good use. Another interesting thing about Python is that the original implementation was already written in Haskell, which means that we can actually compare the two implementations. And it turns out that our rebound-based implementation is more performant than the original one, both in terms of time and space. If you want the actual numbers, once again, please go check the paper. Finally, we can compare rebound to other libraries for verbal binding in Haskell. So we'll have 3 benchmarks here. The first one is going to be this eval one, which reuses the Leonard term that I've showed you in the first part, and it asks every implementation to reduce the term to a value. The second one, NF, is a variant where rather than evaluating the term needs to be fully beta normalized. And the final benchmark, random 15, is a collection of 100 lambda terms, which all need to be fully normalized. So our baseline is going to be the rebound-based implementation. And we can see here that the 2 Leonard benchmark take roughly 4 milliseconds, and the random 15 benchmark is faster, taking 0.5 of a millisecond. So the next 2 implementations use the Unbound library. And quickly, Unbound also offers these generic programming features I've mentioned before. And we can see here that they have a negative impact on performance. But regardless of whether you use that feature, we can see that this implementation is a lot slower than the rebound-based one. The next contender is Foil. That library is based on the idea of the rapier, which is itself used in the GHC compiler. And interestingly enough, this implementation is faster than Unbound on the 2 Leonard benchmarks, but is a fair bit slower on the random 15. But nonetheless, slower than Rebound. The last contender is the Bound library, which is also based on the Brownian indices and uses this idea of, and I quote, making it suck less to make it more efficient. And here it is a bit more efficient than Rebound on the 2 Leonard benchmarks, but is slower on the random 15. So that could be the end of the story. You win some, you lose some. We're more or less on par with Bound. But there is one last thing. I did mention earlier in the talk that Rebound also offered lower level APIs, which allowed you to manipulate delayed substitutions explicitly. And you can actually use these APIs to re-implement these evaluators. And if you do that, you get an implementation which is faster on the random 15 benchmark by a slight margin, but is way faster than every other implementation on the Leonard benchmarks. And even if you use the generic programming to automate some of it, which again slow down your implementation, you still get pretty good performance. So that will be it for this talk. Maybe one last thing I did not have time to talk about, which I think is interesting. I left environments abstract throughout this talk, and there is an interesting conversation to be had on how do you represent and optimize these environments. And we talk about it in the paper, so if you're interested, please check it out. And that's it for me.
Thank you. Of course, we have time for questions.
So you stress the idea of delayed substitutions.
Yes.
And that you, when you do eval, instantiate followed by eval, you're going to kind of fuse them.
Yes.
That was but there's a bit you're sweeping under the rug there because you only make the delayed substitution as a binding. Right, so
yes.
if you've got a big tree of application nodes, then you're going to eagerly instantiate and eagerly eval.
Yes, very much so.
But I think that's a very clever compromise.
Yeah.
Right. So you've got a hook in abstractions.
Yeah.
You didn't really highlight that at all. I think that's the clever compromise that Rebound does.
Yeah.
Is that right?
That's right. So there are 2 things going on here. The first one is, as you said, the bind type is the one type which is not implemented by the user, which means that we can smuggle the delayed substitution at that level without the user knowing about it. The other thing which I did not talk about in this talk, which I think is interesting, is that there is this idea of explicit substitutions. I think that's the right name, where rather than doing this whole thing where you hide substitutions, you make them explicit in your calculus. You add a new constructor to the lambda calculus with substitutions. And we did benchmark it, and this was slower than a rebound. So from going into, or rather profiling that implementation, it seems that if you do that, you end up spending way too much time allocating and garbage collecting everything you allocate. So hiding things at the level of binders has these double benefits that you don't do it all of the time, and we can hide it from the users.
So it seems like quite a clever design, because partly you can hide it from the users, because that's the one type you implement. But also, you sort of chunk it up, so instead of doing a delayed substitution every node, just when you get to an abstraction, and typically abstractions show up quite a lot, but not absolutely. Very, very nice.
Thank you.
Are any of the approaches you benchmark against, non-intrinsically scoped that can tell you, how much overhead is caused by intrinsic scoping?
So here, Unbound is not intrinsically scoped. So sorry, can you ask the second part of your question again?
I'm just wondering how much overhead is caused by intrinsic scoping. So I'm wondering if you compare it with any approach that is not intrinsically scoped that can tell you that.
So my impression of this whole thing is that the part about being intrinsically or extrinsically scoped is kind of independent of the trick we're pulling with the delayed substitutions. The two things are nice to have because you want performance and you want type safety, but I don't think the two of them are you can have one without the other. Actually, what's interesting, and maybe we should do that, is try to benchmark an implementation like Rebound, but without the whole scoping thing. I'd expect similar results, but maybe I'm wrong about it.
Is this like a see. Oh, quickly. Yeah. You sure it's working? Apparently so. Okay. Have you come across the term weak explicit substitutions?
Weak explicit?
Because I think that's exactly what you're doing. And
if that's
search
interesting.
for that, you'll find some literature that I can't remember who did it. But
I will definitely look into that. Thank you very much.
Thank you for the great talk. Can you please give some details on why do you think that the random 15 benchmark seems to behave very differently?
So that's going to be kind of a guess on my side. But the Leonard term that we've been using for benchmarking has actually been around for a while now. In fact, if you look at the slideshow used to present the bound library, they were using that benchmark as well. So what I think happens is that a lot of library, ourselves included, kind of, in a way, optimized for that specific benchmark, whereas the random 15 is, well, random terms. So we could generate other random terms and we might get different behaviors as well, slightly at least.
Okay, thank you.
Okay, we have time for one more quick question, I think.
Yeah, it's a very quick question.
Yeah.
Is it you mentioned that the explicit substitution calculus implementation is slower?
Yeah.
Is it like a publicly available, the implementation?
So we do have that in the paper. So if you want to see the implementation or the numbers, they are there. Yeah, I don't really have anything to add to that.
Okay, thank you for the speaker. And so next up we have Rob, who's going to try to teach GHC that for some classes you always have an instance. Okay, go on.
Rob, this is mostly work that I completed at Imperial College with my then supervisor, now co-author Nick, who unfortunately couldn't be here today. And yeah, I'll get right into it. So the idea of this paper is that we identify a particular programming pattern used in type-level Haskell code involving data kinds and type classes. And we talk about how this pattern is kind of inconvenient to use by default and how we can make it a little bit better with an extension of the language implemented here as a GHC compiler plugin. So traditionally in Haskell, a type class sort of constrains how we can apply a polymorphic function, right? We have a function that can be applied to any type, but only if it satisfies some property for which we need to provide this type class instance, which allows us to then call the methods of that class. But nowadays what we can do is we can have type classes where the parameter is not an ordinary type, but a data kind, so algebraic data at the type level. And in this case, we sometimes end up with type classes that are actually total. That is, they have an instance for every possible type of that kind because they're sort of defined inductively over the structure of that kind. But these type classes, we still have to treat them syntactically as constraints, as like a property that we need to satisfy to call a function, even though we already know we can always satisfy it. And the idea of our implementation basically is to have the compiler treat these total type classes specially by checking that they have this property when the user expects them to, and then by automatically modifying the program during compilation to pass around the runtime evidence for these constraints automatically without the user having to write them, so we can basically think of them as just ordinary functions that happen to take types as inputs. So to see why this makes sense, let's consider briefly what a type class is conceptually. So when you're first learning Haskell, if you read some sort of introductory tutorial, an idea you might encounter is that a type class is just a predicate, right? You might see a sentence like, int belongs to the class show. It's sort of a Boolean property that a type can have, and in that sense, a constraint, when it appears in a function signature, just restricts the choices for a type variable. It filters out some types that don't have that property. But in practice, in the implementation, a type class is more than that because it actually contains data, right? The instances of the class construct the implementation of the methods, and you have to pass that around at runtime. So an instance like showInt is actually like a piece of data, and a constraint is really just another parameter of your function, except it's one that the compiler sort of passes for you via constraint solving. And notice that traditionally this distinction doesn't really matter, right? Since Haskell will only let us have one instance matching a particular type, there's really no way to actually observe this difference because like either an instance exists or it doesn't. As far as the programmer is concerned, it effectively is just a Boolean property. But now let's see what can happen when we use type classes with data kinds. So we'll use this example here. I'm sure you've all seen it before, where we have these type-level natural numbers to sort of statically record the length of the list, which is very useful. And think about what happens when we want to implement some operations on this data type. Say, for example, we want to compute the length of such a vector. We could do the same thing we do for a list and sort of iterate over the vector and count the elements, but that's kind of unsatisfying, right? I mean, sure, we've gone to all this trouble to have the length available statically. It's right there. Why can't we just return it? And of course, we can't actually just return n here because polymorphism in Haskell is implemented via type erasure. So when we run this function at runtime, we don't actually know what n and a were. We only have the data of the vector available. So what we can do to remedy that is use a type class like this isNat here, where we take as a parameter a type-level natural number, and we have a method that just returns the corresponding term. So we just do this sort of like basic recursion over the type to transfer the data from the type level to the term level. And then when we call the method at our type n that we want, then it gives us the corresponding term. But to do that, you can see here we've had to add this constraint isNat to the type signature here to declare that we want to keep that information around at runtime so that we can call this method. But this isn't really constraining anything, right? We're only using it to tell the compiler to hold on to this information. It's not actually telling us anything about how we can call the function because like we know that for any n we can satisfy this constraint. And the idea is basically is that if we can get the compiler to recognize that this property holds, then it should be sound basically for us to have the compiler just figure out that evidence passing bit itself and not have to write the constraint at all. So to formalize that a little bit more, when we have a construct like this, where we have some type variables and a constraint as a precondition and then another constraint on the right, we say that this is a total constraint if whenever we can solve foo A, we can also solve bar A. So you sort of read the statement here as an implication. And notice that this is not the same thing as the quantified constraints feature that exists in Haskell, because we are not talking about whether the constraint solver can produce an evidence term for this constraint, which, for example, in the isNat example, we can't because of type erasure, right? We can't pattern match on the type parameter. But here we're describing sort of meta-theoretically, if the constraint solver can do this, it can also do this. So that we're allowing ourselves to pattern match on A here. And what this property gets us, let's consider we can see, for example, that for all n isNat n is total, right, as we just talked about. And that means that if we have a function like v-length that is parameterized by some type level natural number, and we call it for some concrete natural number, like we have a vector of a specific length here, then we know that we can always get the right constraint by totality. So if we need to add that constraint to the signature of the function, that doesn't actually stop us from applying v-length to any particular vector, right? Because we know there will always be an instance available. On the other hand, if we apply it to some unknown n, say we are ourselves implementing a polymorphic function that takes type level natural number, then we do need to sort of pass that constraint through at runtime. But what we can do is we can just add this isNat n constraint to the signature of the function we're writing, and then sort of delay this problem to when this function is called, and then apply the same logic there. So what we basically want to be able to do is just pretend that we're living in an imaginary world where we don't need to think about type erasure, and we can just like pattern match on a type whenever we want to when we have this sort of total type class. And by this completely mechanical transformation, we can add those missing constraints to our program to pass the evidence around where we need it. And because this transformation is so straightforward, basically, it makes sense to have the compiler do it for us automatically. So this is implemented, as I said, as a GHC plugin. This is what the actual syntax that you write looks like to use this. Somewhat ironically, to declare a total constraint, you use another type class. If you look at this closely, you may notice that we're cheating a little bit here with the syntax. Based on how I defined what a total constraint is, there should be a for all n like there, but instead we're just using an n here and letting GHC infer the for all over there. That doesn't entirely make sense, but we would need to like use an impredicative type to be able to put a quantifier on the inside. And because we can only have these instance declarations at the top level, it's unambiguous what is meant by this, and this just makes it more convenient to type. So when you write this, you are telling our plugin to do two things. First of all, to check that for all n isNat n is in fact a total constraint. And secondly, to automatically add these constraints wherever we are going to need them. It's basically, the plugin behaves like a sort of universal instance where given total constraint C, you can just get C for any instance matching that description. To talk about the implementation, I'm also going to introduce a slightly more complicated example. So here we have a type class where we specify a type level natural number, and then we get a list of that length of some type. And here in the successor case, we require a monoid A instance so we can get a term of that unknown type, right? So here, it would be incorrect to write total constraint list of empty NA, because A could be a type for which we don't have a monoid A instance, right? So that by itself would not be a total constraint, but we can add this precondition here, which again, strictly speaking, would make more sense if it was in there, which tells us that this class is sort of conditionally total. And then when checking, we match that up against the precondition in this instance here, and then that's all good. So I'll go into a bit more detail about how the checking part works. So for a general total constraint, where in practice we could have multiple type variables here or multiple preconditions, there we do 3 separate checks, which together imply that the constraint is total. So the most important thing here is basically what we call exhaustiveness. So if we have any concrete type of this kind, we want to check that it will match some instance of the class, right? What we want to verify is that the instance heads of this class basically cover the whole space of types of this data kind. And if that's not the case, then clearly it can't be total, because then we have a counterexample where we won't be able to get an instance. And that's sort of the main thing, but it's not quite enough. We also check for termination. So if you enable enough compiler extensions with scary names, you can get GHC to let you write an infinite loop of instances, in which case clearly it doesn't make sense to use that as like a proof of totality. So we apply the same heuristic that GHC does by default, which is requiring the recursive occurrences in the context of the instances to be decreasing in some sense. We'll get to it in a second. And then finally, we handle these like preconditions that you can provide for the total constraint and allow those to sort of discharge preconditions of the instances themselves. And
sorry, could you clarify there? 3 doesn't look like a statement in the theorem.
Yeah, so that's basically, if you go back to this one, here we have the monoid A as an additional precondition to be able to use this instance, and we check that the preconditions that you've qualified your total constraint with are sufficient to imply that. So if you left off the monoid A here, you would get an error that for the totality check, you can't satisfy the monoid A there. Like it.
So we need that condition then for it to make sense, but what are you checking when you're checking these 3 conditions?
For the third condition, we're checking that whatever, if you assume whatever is you've provided here, then you can use that to satisfy whatever is required in the instance there. And that's necessary for it to be valid, that like you can use this as an inductive step in your proof here, basically.
Okay.
Right. And so this check is sound but not complete. There's a slightly more elaborate proof in the paper. And yeah, we cover many sort of reasonable inductive principles for these type classes with this. The general case, of course, is undecidable because like type classes are basically Turing complete. You could like make a type class whose instances are the rules of a Turing machine, and then totality checking becomes the halting problem. But we can get pretty far with these sort of heuristics. So to discuss in a bit more detail, for this exhaustiveness check, basically the thing to note here is when you look at the heads of these instances, these are just patterns, right? When you find the right instance to satisfy some constraints, you're basically just doing type-level pattern matching. And because these aren't normal types, but this is a data kind, this can be exhaustive, right? We've covered both of the constructors here. And we already know how to do pattern match checking for functions. We already know how to check whether it's exhaustive. We already know how to find a counterexample. GHC already does that. So basically, we just exploit that fact, and we take these type-level patterns and sort of generate this function where we turn them into equivalent term-level patterns and then just ask GHC if this pattern match is exhaustive. So if, for example, you'd left out the 0 case here, you'd be missing this, and then it would tell you you're missing a 0 case, and then we just transport that information sort of back to the type class, and we get all the benefits of the pattern match checking features that GHC already has. It can find you a counterexample in most cases, and basically here, obviously, it's fairly obvious, but if we had a more complex data kind with more cases, it can help you figure out what case you've missed in your instance declarations, just like it would for a function. For the sort of termination checking for inductive steps, as I said, we're concerned about like instances like this where you sort of use the same thing or have a loop between multiple instances, in which case like that shouldn't be total, right, since the constraint solver won't actually terminate. And we use the same heuristic here that GHC provides by default, which is comparing sort of the syntactic size of the constraints here. So here, because we have an extra constructor attached to the variable, this is larger, and that's sufficient to like determine termination. This is the main source of sort of incompleteness here, given that like there are different orderings we could use that would let us check more than this, but this covers many cases since GHC actually enforces this by default unless you tell it not to, and it's fairly easy for the programmer to understand. And then finally, I mentioned this earlier with the question, but when we have this precondition here, basically all we need to do is check that this is sufficient in order to solve any extra constraints that appear in the contexts of the instances. So when we compare the declaration here to the head of this instance, we apply any substitutions we need, and then we see that the monoid here, the monoid A here will satisfy the monoid A there, and therefore it's okay to have this constraint there. We could be a bit more permissive here. For example, it would make sense to allow other total constraints here to appear here without being listed here if you had like is not n there, but we'll leave that for future work. All right, now I want to get briefly into how the rewriting part works. So that's where we allow the user to basically write code that looks like this and automatically insert the constraints to make it work in the way that the user intended. So if you were to just compile this normally in GHC, obviously you get a type error here saying that this function call gives you a type class constraint that you can't solve. What we do in this situation is our plugin basically intervenes during type checking, and it actually solves this constraint with this sort of placeholder evidence term. This is completely made up syntax, obviously you can't actually write this, where we sort of fill in that instance with a term that just crashes at runtime, right? Like just like how you can write like undefined at the term level, using a plugin we can generate a type class instance that just doesn't actually work, just to sort of satisfy the type checker. And then afterwards, we do a pass over the type checked program and identify all of the places where this has happened. So we'll find the placeholder there, we get rid of it, and we replace it with an actual evidence variable that we attach as a new constraint parameter of the function. And after we do that, basically the AST of the function v-length here will pretty much look exactly as it would have if the user had just written this to begin with, which is what we're trying to achieve, right? Now, if we're just exposing this function to be able to call it in another module, then that's all we need to do. It has the right type. We can expose it. We can call it elsewhere with or without the plugin. That's fine. But if we call it elsewhere in the same file that we've just type checked, then we have a problem, right? Because these calls to v-length down here are now ill-formed. They're in the intermediate representation, they're missing the extra parameter corresponding to the data of this constraint here. So what we do is we do another pass. We search the program for all of the places where this function has been called. And in those, we now we add a new constraint variable there to match up against that extra argument. And then we just run the constraint solver again, taking into account the typing environment in the place where these calls happen and so on, to make sure we create the right constraints. And then once again, we get a missing instance because now we need isNat_n here and we don't have it. So then the process just repeats and we do the same thing here. And we end up with these constraints on this function as well. And this is what we would have written to begin with, and it works just the same way. And we're done. So the examples in this presentation have been sort of a bit artificial, so I'll talk briefly about some more realistic applications. One thing you can use this with is the singletons library, which you may know about, which is a way to sort of use template Haskell to auto-generate these data types that contain the same information in the term and also at the type level, using data kinds to sort of simulate dependent quantification. And one of the things it gives you is this sing_i class, where if you generate the singletons instances for some kind k, then it gives you this class switch, when you restrict it to that kind, it's like the same thing as the isNat example that we were talking about here, basically, but just like more general and generated automatically. And by construction, for any k for which you decide to generate this, it will be total in the same way that isNat was, and our plugin can recognize it as such. And then if you write a bunch of code that has these sing i's everywhere, you can insert those automatically. And of course, many other many other operations on type level data you can then implement in terms of that by taking it to the term level first if you want to. One other case, which was actually my co-author's original motivation for this, is when you're working on an effect system. Often what you'll see in like Haskell effect libraries is you have these type level lists of like functors representing the effects, right? And then every term is parameterized by these type level lists, which means that any operations you want to perform on them actually depend on that type level information, and you need a type class to like merge the lists together or operate on them and all of that. So what ends up happening is that all of your functions call a bunch of these type class methods, and you have like the same constraints with all these type variables in all of your functions. But all you're actually doing is just doing induction over these type level lists, which once again is like trivially total. So you can avoid having to specify all of those constraints everywhere and just be able to call the operations directly as if they were just functions. Yeah, that's basically it. So what we've seen here is that there are a lot of useful sort of programming patterns enabled by using type classes that are parameterized by data kinds, but it's just kind of annoying to use them because they are still type classes and because we have to deal with type erasure. So by doing this fairly like unintrusive modification of the compiler, only touching the front end and the type checked AST, we can make that a little bit more convenient to use. And yeah, that's it.
Thank you. So we actually have plenty of time for questions. I don't know who was first, but let's start with Richard then.
Thanks for the talk. Where does totality enter into the picture? And there's sort of two halves of that question, in that one is, I mean, the transformation that you're describing also would make sense for non-total type classes. And then the other is, had you thought about the fact that there's exotic types? I don't have a better way of saying it. There's types that are like your natural numbers contain things that are not natural numbers, like stuck type families.
Yes. I'll do both of those questions in sequence. So the first question was, why does it make sense to do this specifically for these total type classes? Couldn't we do the same transformation for like any type class? And that's true, but the thing to consider is that for an ordinary type class, we have the sort of additional semantics of the constraints in terms of that it allows us to call the function only at certain types, right? With a total type class, we know that for any concrete call, when we propagate the constraint through our program, right, at some point we'll have a call for some known type, and we know that we can discharge the constraint then using the existing instance declarations that we actually have. Whereas if we did that for a normal type class, if we did it for show, say, you could propagate a show constraint to every function in your program and then end up calling one of them at a type that actually doesn't have a show instance, and then that would be very confusing. And sorry, can you repeat the other question?
About sort of how do you account for types that sort of don't make sense but exist anyway?
So yeah, you can sort of, it's not technically true that induction here implies that for any nat we can have an instance, because you can do things like define a type family with no equations, or that like reduces to itself to sort of create a type of any kind. I claim that you are unlikely to run into this because, in the same sense, right, most functions in Haskell can never actually be total, because you can always have, using laziness, you can always have like a non-terminating term, right? But it's still useful to think that, like, okay, I have this function, and if I apply it to any like term that will actually normalize, then it will return a value. And it's still useful to think of functions as total in that sense. And I think that in the same way, this notion of totality is still valuable to think about, even if you can like summon up an edge case where it breaks.
But it's still safe, right? Like, so for these exotic types, you just get a type error after the plugin runs because there would be a missing instance for
yes. So at the end of the sort of rewriting process, if you end up with a constraint that doesn't actually contain any free variables that are polymorphic in that function, then it sort of detects that something's gone wrong. It's a stuck type family or something like that, and then you'll still just get the normal error that you're missing a type class instance.
Pass it to Simon.
What about higher rank types? Seems that this rewriting thing is just going to be incomplete.
Yes, okay, that's true. We've talked here about the case where we're adding these constraints to the signatures of functions. It is the case that you can sort of witness whether a function actually has a constraint or not by, say, if you have a function whose parameter is a polymorphic function and you were to try to pass, for example, v-length to that, then you can't sort of propagate the addition of the constraint here, since like you might have imported a function from another library that doesn't supply the constraint. That's true. In that case, the rewriting will fail there. And you would have to manually, like, for example, provide like change your higher order function to provide the constraint or something like that. The idea, so indeed we can't like cover all cases like that. The idea here is that we're focusing on the common case where you have a bunch of top-level functions that have a lot of these constraints that you're using everywhere in your program, and we can save the effort of having to do it there. If you write a bunch of functions like this specifically to be able to pass them to some sort of higher order combinator, then yeah, you still have to deal with the problem in that case.
So there's always a bit of a trade-off, isn't there? The more you do implicitly under the rug, the easier it is to get stuck in a situation in which that doesn't quite work, and then you've got to explain to the user what didn't work, and explain to the user a mechanism that they can understand how to fix it. So
that's true.
One trade-off somehow.
Yeah, one particular limitation there is because we're kind of limited to what we can do with the plugin here, since that's how we chose to implement this, we kind of lose the ability to distinguish between a function that's like truly parametric and one that can have these implicit constraints added to it, right? If you could imagine if instead we were choosing to implement this as an extension of the compiler itself and we could just add new syntax, we could perhaps put that information in the quantifier instead. And when we write for all n, which we haven't written here, but you could imagine that we have a different quantifier that says it's okay. I don't care about this function being parametric. It's okay to add constraints depending on this variable.
Thank you for the talk. I wonder if there is any like a planned future work on this thing, because like, for example, for example, the mutual recursion would not work for this system, right?
Yes, so that's true. There are some cases in the checking part especially where it's not like a fundamental limitation like what we just talked about, but like there are some edge cases that we haven't covered, like I said, with other total constraints, or yes, you could have mutual recursion between type classes as well. Yeah, that's definitely a direction that could be considered for future work. There are more sort of advanced ways that you could structure your type class instances such that they are still total sort of by induction, but in a less, in a more complex sense.
Okay, thank you for answer.
Time for one quick one more.
Thanks for the talk. I'm curious how this works across module boundaries. Like if you import one of these functions, will the function have the constraint in them?
Oh yes, that actually just kind of works fine out of the box before we even do this like propagation part. The question was, does it work across module boundaries? And yeah, basically, when we modify the type of v-length here during, like at the end of the type checking process, that's still like right before we determine what type will be exposed from the module. So if we then call this from another module, it will have the constraint in it, which means if that other module is being compiled without the plugin, then you can just call it normally as if it has this type and you provide the constraint. And if you are also using the plugin in that other module, then you can automatically fill in and propagate the constraint there as well, just like when calling a type class method directly. So there's interoperability in both directions. You can combine modules compiled with or without the plugin.
That works really well, yeah. I'm thinking of like languages like Idris where they have like selective type erasure, where it's kind of like you can add it in or you don't add it in. I think this matches that like usability pretty well, I think, those languages. Thank you.
Okay, thank you. So next up we have Justin, who's going to tell about his experience in applying Haskell to a domain that is not usually done with Haskell.
Yeah, hi everyone. My name is Justin Lay. I'm playing on behalf of Anduril. We've been doing embedded Haskell for a long time in real-time systems. And the first thing people ask me when they hear what I'm doing Haskell embedded system is, first of all, like, what does that even mean? Like, how does Haskell run on a chip or anything? So we have accumulated a lot of tough lessons learned, a lot of general principles we've built over the years, and it's kind of a quick, rapid-fire knowledge dump and experience report. So I've it's not a structure, it's kind of just, I've made 3 general categories of lessons and areas that are worth looking at. And if you have questions at the end, I'll kind of clarify, but this is more like a knowledge dump and experience report than like a unified, nice, tidy little bow of things. And so why Haskell? Haskell started before I came there, almost at the start of the company, actually. So we had kind of a lot of requirements within the project. We needed to coordinate sensors, peripherals, and other outputs, FPGAs, CUDA cores, all that, and low flow systems, which are usually interfaced using C in most languages. We need the layer of orchestration between those things to be very reliable, and we need to be able to encode business logic very well in a way that there's no logic errors or crashes. We need to deploy this across multiple heterogeneous machines with different capabilities, with different hardware, even different architectures between like x86, Arch Linux. And we need to have multiple devices, multiple products that each deploy very differently. So I think overall the question, why Haskell? I think if you're here, you probably know the answer is why not Haskell, right? If you're here, you definitely have the drive to put Haskell everywhere. I think it works very well because the low-level embedded programs, CUDA code, the FPGAs, the serial bus interfaces, everything else runs below the socket level, below the kernel level, but the Haskell is what orchestrates them all together. And we need that layer to be very, very secure, very type-safe, and very reliable. And it's kind of a little graphic of one device has multiple machines on them. Each of them are different Linux boxes. They're running NixOS. So the machines, they have sensors, they have GPUs, all interfaces using sockets or serial buses, some even using USB. All very low-level interfaces. They bubble up through the Linux kernel, and Haskell lives right on top of that in whatever memory we have left on the machine. So the Haskell space does have, the full Linux. We have RAM, so we're not constrained in terms of the Haskell aspect, but we don't have a lot of RAM. We have just a limited amount. We can't just write memory leaks forever. Our things have long-living processes. So we have one device, multiple machines. These devices here have low-level things. Some of them are just purely Haskell devices that only run Haskell processes, Haskell daemons, Haskell servers. We even have some devices that have to serve the UI to users, and they run Haskell backends within the same device. We're working on using Haskell in the UI as well with JCJS. So hopefully this can become more and more Haskell. Maybe one day there'll be even more Haskell in the kernel as well. So this is what we mean when we meant Haskell, embedded Haskell. Not like, we're not writing FPGAs in Haskell yet, but we are servicing the orchestration layer and the process between everything in Haskell. So some lessons on the low-level aspects. Haskell is actually the best C build system we've used, or Cabal is. Cabal is really great with integrating extra libraries, extra source files. So if you ever need a C build system, even if you're not using Haskell, I would just use Cabal anyways. Everything works so well. There's been a lot of great work. It even builds C++ very well too. So C++, everything integrates very well with Cabal. So if you're working with C code, Cabal is great. There's so much work on that. Everything we've built is orchestrated using Nix and NixOS. I know there's a big overlap between NixOS people and Haskell people. This is like where it all works out very well. So all the firmware, all the integration with the foreign headers that Haskell pulls in through FFI, NixOS handles very well. We do a lot of code gen using NixOS that's integrated into the Haskell system. So NixOS can read documentation, can read module specifications, it can read C bindings, generate those bindings as Haskell libraries, and now those live inside your local package. So you can just add in a C header library, hopefully even more smoothly with well-typed HS bindgen. So you import your C library as if it was a Haskell library, and it lives in your Haskell space right away with NixOS. And there's a lot of fiddling with CUDA and Accelerate that is really tough using multiple systems, heterogeneous systems, and NixOS handles that very well. So we don't have to worry about any CUDA dependency mismatches. It all just works out of the box. We try never to use the D word. We don't use Docker. Everything is within NixOS. So using the most recent Linux features, systemd, C groups, Haskell running as systemd processes, and with Nix, everything just works well together. I can't imagine a better glue layer than Haskell for business logic. And yeah, we definitely leverage Linux. We have shared memory buffers in the RTS, so Haskell has the ability to copy off shared memory, so multiple Haskell processes can share memory with each other. So you can pull, so let's say you have a sensor that detects maybe data from a room, like heat temperature. You can get that off the FPGA right away in PCI bus, pass it to detectors across your whole process, your whole computer, your whole OS, and never do any single copy. So zero copy sharing between FPGA, PCIe, and all your actual data processing systems because of how well Haskell integrates with the Linux runtime and API. Some unfortunate lessons we had to learn early is definitely instrument early. There's a lot of nice Haskell libraries for instrumentation if you're not aware of them. EKG and StatC are great out-of-the-box solutions for very easy instrumentation and monitoring. Those hook up straight to the Grafana and other UI systems that you can just have a nice dashboard right away. There's no kind of upfront work to be done, very little. So it's just as integrated as most other ecosystems. And also with Brick, building TUIs is super simple, right? If you've ever used a Brick TUI, the startup time from pulling in data streams to having a fully functional TUI is very small. Sorry, a terminal UI. So it's a graphical on the terminal with libraries like a GHCUP, like graphical interfaces on the terminal. So I guess I wish I had an example, but just terminal interfaces, yeah, graphical terminal interfaces. And also it's good to respect the hierarchy. Cycles at our level are cheap, threads are cheap, but FFI and I are expensive. So utilize thread scope, and GDB works very well as well. GDB works very well with Haskell processes in case you haven't tried it. Thread scope helps you very easily spot FFI syncs. There's a big potential for FFI between C processes to lock the whole system, the whole runtime together. And it's really easy to spot those in GDB and thread scope and just eliminate them right away. There's not much headache and it's easy to just dig into them. It's not as bad as you might expect. It's good to, another lesson is have progressive capabilities, right? Haskell, you can serve many different types of servers. We end up serving gRPC and HTTP2 for our interop with other devices. We have Servant, HTTP1, very simple to have simple web sockets and other servers like that. At the low level, we have things like raw TCP using CBOR for incremental deserialization. If you ever use the libraries like Serialize, they let you give message framing. So you can have very efficient binary serialization in Haskell very well between processes. And another low-level thing are hooks on actual file descriptors. So if the top level fails, if the UI fails, if the HTTP2 fails, we have HTTP1. If HTTP1 fails, we have TCP. If TCP fails, we have file descriptor hooks. So at each level, there's progressive safety and assurity. So your very important processes that need to keep running, we have things like CBOR and Serialize on TCP. The very high-level things that can break down, maybe UI might break down. UI can be allowed to fail. We have higher interfaces for that. And the Haskell runtime is very good at balancing out those different layers of failure. And as long as you keep tight handshakes across procedures, Haskell's greatest strength is type safety is across the board useful. We have type safe TCP, type safe file descriptors. Never forget why we're using Haskell. It's for that nice type safety. Along that line, I think I want to say what we agree as a whole company is Haskell's #1 killer feature. Anyone want to take a guess? I gave some examples, but the real answer is not here. Yes?
STM?
You did guess. It was STM. It is STM. By far, it's the most bang for the buck in terms of working with these type of things. Why? Because we have an STM universe, and everything works together very well into a nice denotative system. No need to have extra libraries. It just all fits together pretty well. Between pure STM, we have concurrency. We have hardware STM, which we use STM to wait on file descriptors across memory, across hardware. You have time-based STM. The whole universe works all very well together. It's just kind of a beautiful way of describing the whole system. Everything hooks in. The more we hook into it, the more we can use from it. So it's like an N-squared type of networking effect of benefits. Let's see, like a little bit of control flow. Workers, we want to avoid immortal threads, maintain system coherence instead. All this is done using STM. We really don't use monad transformers that much. We like just having context to IOA. It's kind of enough for a lot of things. Streaming combinators, when I first started, I streamed everything combinator that used every library I could think of, and over the years, I've rolled them back. They're very useful and powerful for prototyping, but if you know what you want, just writing the quick loops ends up being much more effective. So I love streaming combinator libraries. I built a lot of my career on them, but the more flexibility you get, when you know what you actually want, you start rolling them back, and they roll back pretty closely well to like actual real-time loops. Lifetime management using with X bracket continuations works well, and remember to use resource T and acquire for scoped regions of memory. Do not be tempted to use these to manage heap memory. These only manage kind of external life cycles. We have issues with like people using resource T for heap memory management, but it's more for life cycles and resources. And kind of the final wrap up, every Haskell there's two goals, I'd like to say. This is definitely my daily journey. We want to build beautiful type-safe abstractions with clean semantics, or we want to just have like psycho safety, make it simple as possible and usable. And it's a constant battle, even in the industry. Here's some quick summaries on Haskell language features that we've tried out and rolled back. Compiler optimizations, we definitely assumed a lot of optimizations that didn't happen. So we had to go back and manually vectorize, manually optimize, manually inline. It's not magic, but it's pretty close to magic, but it's not 100% magic. We get a lot of bang for buck out of dependent types using length index types and state index types. A lot of times, building these bindings for C APIs, having those types clarifies the APIs very well for anyone to use. But always provide a nice untyped interface for people who just want to do things unsafely. Our configuration is type safe. We use a type safe configuration language that isn't Haskell, and it supports GATs. So if your config language is safe, you can actually integrate everything. The whole system of configuring your systems and everything is also type safe, and you don't have the mismatch. So you get a lot of benefit out of that. And when we have CUDA and accelerate using CUDA disconnect compilation, we definitely have more type safety there. So there's a lot more that can be built into the type safe world than you might think initially. Some closing thoughts. I think it's nice to say a simple Haskell scales for just using simple procedures, simple I/O actions, and context passing along. It definitely goes a long way. STM is in base, and it definitely goes a long way as well. The synergy you get out of Haskell, Nix, and Linux is very hard to understate, how things just fit together so well. And a lot of great work has been done into making that airtight, and I really appreciate it. STM definitely, I think, is GT's greatest asset for this type of project. We want to emphasize using progressive capabilities for reliability. Things can fail, but make sure that there's always a level that doesn't fail and can be in Haskell. Manage your resources principally, and never abandon type safety totally. Yeah, that's my rapid fire. Any questions, but hopefully I've convinced you, if you're doing embedded work or work with very fast systems, memory systems like CUDA, FPGA, then this gives you the confidence to start that at your own company.
Thank you. We have time for questions, and in the meantime, Phil, can you set up, because you just... So, questions from the audience? Okay, they're on the platform.
Yeah.
Whenever you have embedded Haskell, the thing I worry about is like memory and garbage collection and things like that. Is that not a concern for you?
Yeah, the underlying systems are written in FPGA or other fast libraries in C sometimes, or CUDA. The Haskell layer is simply the orchestration. So as long as you keep your actual memory in the Linux space and on a heap clean, then as long as the orchestration stays safe, then you have a lot of room for memory usage.
Hello, is this on? Okay, thank you for that good talk. You said that you use Nix, and in my experience working on GHC, also using Nix and Flakes, I have to run Nix collect garbage-d quite frequently. So I'm wondering what your experience with the Nix packages and Haskell Nix ecosystem is, if you can comment on this.
Yeah, the development process, if you can, a single closure, we have a lot of room. We usually we can go months without like a garbage collect side of the closure. The main things are upgrading the CUDA dependencies. That's like a huge chunk of space for some reason. But as long as you don't update that very often, then it's very easy to maintain sharing. There's a lot of like sharing between NixOS, right? Most libraries are shared. There's no extra space needed for that.
Can you say more what you mean by the STM universe?
The STM universe
is kind of like it's a library with some powerful combinators for concurrency, but I get the impression that you've built some kind of library infrastructure underneath that you might want to share.
Yeah, actually, we haven't built that much, but we're using things that other people have built, right? There's the async library, which uses STM to manage threads and workers. The STM manages file descriptors pretty well. You can wait on file descriptors, wait on hardware inputs. So within one atomically block, you can call across I/O, hardware, threads, all managed in one nice atomically, right? So if I want to wait on this descriptor, this hardware, this thread, and this message externally, they can all be done in one single atomically, if that makes sense. So the more you get out of that, the more n-squared network effects you get out of the benefits there.
I don't think there's a paper associated with this talk. Is there somewhere with more details on the the implementation details of how you've done these things. It feels like you've got some recipes that could be reused by people, and I want them.
Yeah, there isn't yet, but if there's interest, I will work on like doing some more publishing work. I do run my blog, and I'll try to update things as I can.
I would appreciate that. I love your blog a lot.
Yeah.
Okay, any other? Okay, well, in that case, I have a question. So I imagine that the more you can cover with Haskell in this distributed and very multi-component system, the easier your life would be. So which would be the number one area where you can't apply Haskell, where GHC doesn't work out, or maybe you even tried and it didn't work out? What would be the number one where you wish that Haskell could expand into in this heterogeneous system?
That's a good question. We are working on getting Haskell more smoothly in the UI aspect of it. Haskell in the FPGA would be nice. But there's actually very little code.
I know someone who could
Yeah, of course. And we're actually slowly converting things into Haskell all the time. Like we recently converted a bunch of kind of LabVIEW code into Haskell, and just overall, just it's a slow process, a slow march of eating up everything we can, because we're very hungry.
Okay, thank you. Thank you, speaker again. For the final talk of the morning session, we have Phil with what I expect to be a quite controversial proposal.
So it's delightful to be able to speak at the Haskell workshop again. Earlier this week, I spoke at ICFP. Do I use this? Earlier this week, I spoke at ICFP, and there were about this many people, but it's a huge room, so it felt empty. Right? This feels much more, I hope, warm and welcoming. So this is just a talk, but it is written down in my blog. And we're just going to use the blog to show what I'm talking about. So basically, one night I was trying to sleep. I thought back over regrets. And this was a regret about something that never got in to Haskell. And maybe at the end of this, you'll think they're very good reasons it never got in to Haskell. But what I'm hoping is somebody here will think, oh, that's sort of cool. Maybe I want to do something with it. So the whole reason for doing research is so that other people can pick up on it. I'm hoping to inspire some of that here, because I'm retired now. So I'd be very happy to work with somebody. But no, I'm not going to go in and modify the Haskell compiler. So before there was Haskell, there was something called Orwell, which was sort of a dry run at Haskell, which I had done at Oxford, working with other people. And Orwell had this feature that if you, the order of the equation shouldn't matter. So if you want to write equality, right, nil equals nil is true, x cons x's equals y cons y's, if x is equal to x's and x is equal to y, else, if in any other case, equal false. So this is a wild card, of course. So if I say something you don't understand, please do ask a question. If I say something you disagree with, wait till the end to ask a question. So, and you know, it's not just for list, right? We have two shapes, right? We would use, so this is not what Orwell looked like. Orwell looked more like Miranda and had an if and the condition at the end. But thanks to Paul Hudak, we now write our conditionals this way, so I'll show it this way. And if x is equal to y, and they're both circles, then check that the radiuses are equal. If they're both squares, check that their sides are equal, and otherwise return false. And again, you needed this else clause there. But sometimes you might not want to use an else because either one is perfectly fine, but they overlap. It's like we're defining plus of x and y, and if x is 0, then just return y. If y is 0, just return x. They could, of course, both be 0. But that will be all right, because if they're both 0, we'll return one of these two things, and they're both 0, so they're the same. But we're just asserting that implicitly. We're not checking it. So, right, well, what would it look like to check it? Well, if you'd write down this, but it would compile into something much larger. If x is 0 and y is 0, and x is equal to y, then return x. But if they're both 0 and they're not equal, something went wrong, so return an error message. Sorry, this is wrapped around because that's just the way the blog displays things, alas. And then if one is 0 and the other one is not 0, you know what to do. And if they're both not 0, then we go and do the otherwise clause. But we didn't put this in Haskell, so for two reasons. One is it's weird, right? And you don't want too much weird in a new language or people will just stay away. So we left that out, and it sort of worked. People came after a while. The other reason is sometimes you do want the behavior Haskell gives you, which is just to do the equations in order. But of course, in that case, which should be pretty easy, you'd have to put an else between every equation, which just looked really ugly. So I was tossing and turning in the night, and a solution occurred to me. It wasn't a solution to any of the semantic issues, but just to the syntactic issue, because sometimes that really gets in the way. I suddenly went, I could have done this. That would be nice. So the idea is, right, we can do bar otherwise, but otherwise, right, otherwise in Haskell is just a variable in the standard library bound to true, right, because it just says, okay, you've fallen through the end, just do it. What if we made otherwise into a keyword? So this is incompatible with what's in Haskell now. You need some pragma, and if you're using this pragma, it wouldn't quite fit with the other code, which is, again, annoying. It'd be nice to be backward compatible in some way. So now we would just write equality like this, with bar otherwise at the end, and the square example is very similar. And the plus example now is very similar. If you wanted to get back the old behavior, right, then you would say otherwise and follow it with a condition. That would be okay. Or in the cascading example I gave, right, we would just add otherwises before all the other conditions. Otherwise is sort of lengthy. Some people said, oh, why don't you use else or something instead? I won't get down to that level, but there might be better ways of doing it. And just to give an example that's a little bit more complicated, right, if you said something like P of x and Q of x, otherwise R of x or S of x, otherwise T of x, then we've got two groups here, and within each group we have this same behavior. So we're just breaking things into little groups. Sorry?
What's neat?
You will find out shortly. That was where I got to, and I wrote it down. I sent it off to John and Simon. This was actually not recently that I had this tossing, turning in the night and came up with this. It was 4 years ago. And I discovered the reason for writing this stuff. So Simon just didn't like it, alas, or else it would be there by now because Simon's very quick at doing things. But I discovered the reason for writing things down, which is then John Hughes can comment on them. So, write stuff down because John or somebody like John will then give you useful feedback. So in fact, John wrote back an interesting answer, and rather than me telling you, as I did in the blog, what John's interesting answer is, I will let John tell you what John's interesting answer is.
Okay, so when I saw this, it looks very nice, but there are one or two things that worried me connected with laziness. And in particular, if you think of this translation that you've seen in which when equations overlap, equality tests get introduced, the obvious question is, well, what if the result is an infinite list? That equality test may itself cause the function not to terminate. And so the suggestion that I made several years ago was that instead of performing an equality test, just introduce a meet operation. And what meet does is it takes two lazy values and traverses them, and as long as they are equal, it returns that part of the result. But if they become different, then it returns bottom. So you get, it's the domain theoretic meet of two values. And you have it somewhere in your blog. Right. So for integers, of course, which are an atomic type, then it's just the integer, if they are equal. So it's essentially the same as equality. Otherwise, it's undefined. But if you had a lazy list, then you would be... Okay, then nil meet nil is nil, but when you have conses, then you can independently take the meat of the heads and the tails, and thus you preserve the lazy behavior of the function. So I thought making this change would enable functions with infinite results to behave in a way more like the way they behave at the moment. Meet would need to be a class, and the compiler would need to introduce calls to meet in appropriate situations. Do you want to step back in now, or shall I go on to left-rightness?
Let's do it chronologically, so you're next.
Okay, so in that case, I would like to go down to the comment I added last night. Where does that start?
Well, the one you added last night, just above this one.
Just above this
one? The one by Anonymous.
Oh.
You forgot to identify yourself.
Oh, I'm sorry about that.
There it is. Anonymous said.
Okay, can we make it bigger?
Yes. What is it? Shift, Control. Oh. Oh, Command.
Yes, so I am also a little bit worried about the interaction of this design with laziness and in particular pattern matching order. So if we just consider this definition here, right, that is perfectly valid Haskell today, you might ask yourselves, what is f of bottom and true? Right? And if you look at the first equation, it's clear that it should return, oh, A. Did I really say A? Oh, well, it's A. With this idea, we have to go on and try to match the other equations in the same commutative group, or the same unordered group. That means we have to match the second equation as well. And when we match using Haskell's existing left-to-right pattern matching, we have to start by matching true against bottom. And that hits the bottom, so that means that the semantics of this definition would change, right? And f of bottom and true would have to return bottom instead of A. Which seems a little bit disturbing. So, of course, in this case, using right-to-left pattern matching instead would solve the problem. And so Phil was suggesting that we just let the compiler choose the appropriate order.
Not exactly. No, I said that one point, and then you came up with a counterexample that pointed out that won't work very well.
Okay. Yes.
So maybe I should show my thing and then you should...
Yeah, go on.
So what I had in mind, right, the whole point of this is top to bottom doesn't matter unless you plopped in an otherwise. So maybe left to right versus right to left shouldn't matter as well. So what would that look like? Right, if you define, there are two ways of defining or then, right? This sort of standard way, where you look at the left one first, right? So if it's false and x, you get x. If it's true and x, you get true. Or, right, we could do it the other way around, right? Look at the second argument first. And, right, so this way, if we put in a bottom after the thing that we're looking at, it's fine. But if we put in before the thing we're looking at, then of course you get bottom. And the same for this. So there's a standard algorithm for doing this, which you can find in the chapter on pattern matching in Simon's book on implementation. I saw somebody quoting that very positively the other day. I thought, oh, that's very nice, except they cited you as the author. I wrote that chapter. But anyhow, there's a standard algorithm for doing this. Not clear how well it interacts with laziness. John and I were just discussing, we thought maybe really the right thing is not to allow overlap at all, which is just what Agda does. And of course, the nice thing is if you're using Agda and Emacs and they do overlap, it gives you some feedback, which is really nice. Doing this takes you further away from just looking at the code and knowing what it does. So having some feedback would be helpful. And then John had some additional interesting ideas, which I will let him finish with, because we need to wind up quickly.
Okay. So which interesting idea were you referring to, I wonder? So one of the things that I was worried about was considering, where is it? So consider this example at the top there. Right. So here, then, there is no evident pattern matching order that one might choose. I mean, would you choose left to right or right to left? The patterns give you no clue. And this is the example which I think I don't have any good solution for.
John, maybe what we should do is for the additional stuff, let people look at the blog if they want more details, but maybe we should stop now.
Yeah, okay.
Does anybody have any questions?
Yeah, thanks. That's great.
Hello. Thank you. Great talk. I couldn't help but notice that I think the definition was called OR-L, and that was exactly Plotkin's parallel OR. And I'm sure you're aware of that.
Plotkin's parallel OR is more like the, more like this one.
That one. That's the one I thought about. And it seems that the identified problem with that parallel OR is exactly what you're talking about here, that there's no canonical order or correct order, no possible order in which to evaluate the arguments. One solution to that is Girard's stable functions, where this alternative is rejected exactly because you cannot find such a possible order. So I couldn't help but notice, it seems you're doing exactly the same thing here as with stable functions.
Yes, I think that's exactly right, and that's a really good connection to draw. Thank you.
So I think perhaps this is this may be the example that or the idea that you intended me to talk about, which is that the problem here is that left to right pattern matching order, or any pattern matching order, gives different semantics. So there is no sequential ordering that can implement this first definition of OR. So my proposal was that one restrict groups of equations so that all the equations in the group have the same pattern matching order. Now, in this case, since the last one matches on both arguments, that means all of them must match on both arguments. Of course, we'd want to write or true and then an underscore, but if we use a bang, as in the definition at the bottom, then we get the same strictness. So we get the same strictness in every equation, and by doing so, it then doesn't matter whether, it's a way of kind of finessing the problem.
Thank you. This one? Okay. This reminded me, this is nice, but slightly related. I would actually care about if we had OR patterns in Haskell. This looks like I thought a bit about how to get OR patterns, and a lot of stuff seems to be similar, and that how would it interact if you had OR patterns?
Well, I mean, we did an example with OR, but I don't think...
No, not OR as a logical thing, but like OR pattern.
I think I know what you mean by OR patterns, right?
Okay.
Where P bar Q, and it says here it can match either P or match Q.
Yeah.
And that's an interesting feature, but I think that's possibly orthogonal to what we're talking about.
Okay, it doesn't make any extra complications?
I don't know whether it makes extra complications or not.
Okay.
So it seems the way this meet class works is that it will, if things don't meet, then it will fail at runtime, right? So that means like your program could crash at a random point, like at runtime, perhaps in production. So that seems to like somewhat defeats the purpose of making it more type safe, because it's not making it more type safe, right? It just makes it crash, right?
That's true.
All right, thanks.
It means if something happens that you didn't expect, instead of just getting a random answer, you know, either X or Y where they differ, it would crash and let you know something was wrong. So, right, some people think that's horrible, you never want it to crash. It's better if it just gives a wrong answer. But for many applications, like the ones you and I work on for I/O, that's maybe not a good idea.
So there's a certain element, the cure might be worse than the disease, right? So the disease is the order of equations matters. And so it would be nice to have the order of equations not mattering. But in exchange for making the order of equations not matter, we've got to explain something much more complicated to programmers about what the semantics of the program is and what the program means. Whereas I can be done with pattern matching. I say, equations mapped top to bottom, left to right. You know, job done, 30 seconds later, everybody knows how pattern match. That is an advantage, right? There's a cost that equation order matters. So I just pointing out there's a balance here. It's not an uncontrovertible good. And the other sort of slightly unrelated point is that there's another reason why left to right pattern matching, specifying that rather than specifying some arbitrary order, can be helpful. It supports view patterns, in which maybe matching on one can bring into scope a variable that you use in the next, but also GADT matching. You might match on a pattern that makes a type constraint that makes the second pattern exhaustive. I'm not quite sure what happens if you try to match that in the other order. So these things interact.
So in terms of the cure might be worse than the disease, as I thought through this, I think that might be right. And that this idea of, oh, any of them might match, and if two of them match, we'll check that they're giving the same answer. Maybe that's just overkill and not the best for the, you know, this is for the cases where you want stuff that you're pretty sure works. And maybe a much better solution is, as I mentioned, the one you find ADDA, which says, okay, if you've got a group of things without an otherwise, then for the group of things without the otherwise, they better just not overlap. And they must be distinct. And we know how to check that. We even know how to check that with the GADT dependencies you mentioned, because So then this would just be a suggestion for the bar otherwise or something similar as a compact way of saying, here the order matters. So in AGDA, you just write them and they're supposed to go in order, but if the order matters, it tells you, it gives you feedback. Here you write it, you know, this would be a new syntax for AGDA say, where you can say, here I think the order matters, and the other places it doesn't. You don't need feedback. You're telling it, and if not, it gives you an error. And just for the audience as a whole, right, the way I explain all this to my students here, the fact that looking at AGDA can be quite good and give you lots of good ideas is, AGDA is what Haskell wants to be when it grows up.
I think it's also important to remember that the question of whether order of equations matters and whether order of pattern matching matters, those are two separate questions. So you can perfectly well use left to right pattern matching, partly for the reasons that you bring up, and still try and make the order of equations not matter.
You brought it up, not me.
So this is not fully formed thought, that it feels to me like the equality that you want to use in these checks is like this Platonic nebulous equality that people use in equation of proofs, and not the term level, you know, A to A to bool equality that you get from Wiki.
Well, this is for doing, right, this would sort of let you write down something quickly and then get some runtime checking. But maybe that space in the design space is less important, and the spaces at the end where, you know, run fast and break things, which is sort of what Haskell corresponds to, or do a little bit of extra work, you're less expressive, but you're more sure of what's going on, which is sort of what AGDA corresponds to. Maybe those are the two good points. And the point I talked about here isn't the best point, but still the bar otherwise syntax is useful.
Yeah, it just worries me that the like putting a user-written type class instance at such a foundation of point of of the semantics of pattern matching is to me a bit fishy.
Just in regard to the person who asked about OR patterns, there's a very nice paper recently, and alas, I cannot remember the title of it, that talks about OR patterns and AND patterns in a very comprehensive way. I will put a citation to it as a comment on the blog. But one of the reviewers for this conference said, ooh, you should cite this paper, and they're right, so I will go back and add that citation.
Okay, last quick one, hopefully.
Parallel OR is good because it allows us to write more terminating programs.
Yes.
And it can actually be implemented in Haskell. A variant of John Hughes's neat has actually been written up in a blog post in 2008 by Conal Elliott with his unam operator. You can race the two branches of OR, and whichever yields a value first. Yeah.
So you can imagine a compiler that inserts parallelism when it sees definitions of this sort. But note that you can't insert sparks because the scheduler may not throw away any of these parallel executions. You really have to start Haskell threads for that. And starting Haskell threads is cheap, but it's not so cheap that you want it to be part of the implementation of pattern matching. I mean, I would guess that it is hundreds of times as expensive. Simon, does that sound plausible?
It's implementable, but it's a big step up. So I think, again, the cure is worse than the disease.
So when you write parallel functional programs, the first thing you have to think about is controlling granularity, so that you only start parallel tasks very, very occasionally. And starting a thread inserted by the compiler just because you happen to write equations that overlap, no, I would not turn that flag on.
So we're slightly over time, but it's only lunchtime, so anyone who wants to get food, feel free, but we can just let Alex ask his question. I think it's fine.
It feels like implicit in this whole discussion is that we are targeting a sequential hardware where we have to choose in ordering. If we had hardware that allowed us to efficiently start evaluating things in parallel, and I'm not talking about multiple threads, but I don't know, graph reduction or something where you could evaluate both sides of the OR at the same time until one of them has returned. It feels like we're pushing a lot of the semantics of the hardware into what's going on here, and it feels like there could be something that you could target that allows some of the ideas that you're talking about here by not restricting ourselves to saying we have to do this and then this and then this and then this. Is that a reasonable thing to think? I don't know what the hardware looks like.
So I think it's a priori reasonable. If we had fine-grained parallel hardware and we could just evaluate things in parallel, life would be great. That was the dream in the 80s. People have been trying to do it for a long time since then, and it has not won out. I don't think it will win out on this occasion either.
It'll happen eventually.
Okay, thanks again for our speakers, and that concludes the morning session.
1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Is there voice from the speaker? I think so, right? Mm-hmm. 1, 2. Hello? 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 1, 2, 1, 2, 1, 2, 3, 1, 2, 3. I think this is better, right? Yeah. I think we do want to increase the, okay. One, two, 1, 2, 1, 2, 1, 2, 1, 2. Hello? 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 1, 2. Hello. This is good. 1, 2. Hello. Hello. Yeah, I think it's better, right?
There's a little hiss out there. So did you increase the gain too much?
1, 2. 1, 2. Better?
No, the volume is there, but there's a
Hello? Hello? Hello, 1, 2, 1, 2. Hello? Testing. Can you hear me? No? What's up?
I think it's fine.
It's okay? Should I check the screen?
1, 2.
For the hissing thing?
1, 2. 1, 2. 1, 2. Hello, testing. Testing. 1, 2. Is there a, I think it's okay. Hello. Let me also stand next to the,
Hey, can you mute them?
mute this.
Yes, just to isolate them whether this is causing the hissing.
Okay. Yeah, not a problem. Okay, this is now 1, 2. Hello. 1, 2. This is good? Yeah. Yeah, okay.
Hi, hi, hi.
Testing, blah, 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 blah. Oh, that sounds good. Something's happening. No? No, there's definitely something happening. Yes. Oh. I can't tell if it's loud enough, but I'm definitely getting amplified.
Sure. So we will do an audio test, just 2 more minutes. Keep talking. This one works.
Like, I don't want to be lost with a recording or something like that. Like, if that's, I'd rather choose the safer option if we're not sure. What was that? Yeah. Yeah.
I can just give this to you.
Or
Up them down.
just pass.
Yeah. Hello, everyone. Welcome to our second keynote at the Haskell Symposium. It's my great honor to introduce Richard Eisenberg. Richard is currently a language designer and software engineer at GenStreet, working on the OCaml language and its implementation. Prior to joining GenStreet in 2022, Richard was a core contributor to GHC and Haskell ecosystem. I worked with Richard in 2019, and we had a paper together, which is still, I think, one of my most beautiful papers. Richard earned his PhD from the University of Pennsylvania in 2016, working with Professor Stephanie Warwick. Before getting his PhD, he was a full-time secondary school teacher, since he has taught at the Bryn Mawr College and worked as a researcher for Twig. And Richard was a founding director and initial chair of the Haskell Foundation, a nonprofit formed to support the language and its ecosystem. Being a person worked both on Haskell and OCaml, I'm very excited to hear what Richard is going to tell us. Please take it away.
Thanks for coming, everybody. I was hoping to say that there are seats down in front, but there's maybe one or two, not too many. I don't know. So thanks for joining us this afternoon. Ning actually summarized a lot of the things that I'm gonna start with, but we'll get there in just a moment. So my goal, the big goal of this keynote, is to spark conversation, right? So this is about Haskell, this is about OCaml, but mostly what I want to get out of this is more ways that these two communities can talk to each other. This has been something I've been interested in for years before joining GenStreet also, and to foster that communication. So that's really what this is about. But I need your help to do this. So that means that not only is it going to be conversations that happen after this, but conversations that happen during this keynote. So please raise your hand. I'm going to be having opinions in here. Maybe you disagree with those opinions. Maybe you'd like another spin on things. That's great. We can all sort of start this conversation together. I would much rather lose a few slides from my talk and have better conversation than to be able to get through every single small point that I had sort of lined up in here. So please do participate. Okay, I'd like to set a little bit of context here. Again, Ning sort of said much of this. So the context here is that I started to think about Haskell and to get involved with Haskell when I started my PhD. I enrolled in advanced functional programming at Penn under Stephanie Wyrick, and right away was just amazed by this language. So I had been programming, I'm not going to do the math, for a while at that point. But what I realized when I learned Haskell is that actually my entire life I've just been programming in Haskell, but in translation. So I spent a while doing a fair amount of Java programming, but actually without realizing what I was doing, I was always trying to do sort of pure functional programming in Java, which is kind of a strange thing to do, but that's just like, of course that's the right way to do it. So when I finally got to Haskell, I was like, this is really what I've been looking for the entire time. And so that was great. So I started a research program with Stephanie, and then pretty soon Stephanie introduced me to Simon, which was great because the research program that I was doing, I wanted to add more support for dependent types in Haskell, and then the first step to do that, I was going to make this template Haskell version of dependent types, which became eventually the Singletons library. And to do so, I needed more support in GHC than GHC had, so I quickly decided, this just isn't going to work out. But then Stephanie said, why don't you just, contribute to GHC? And I thought, who, me? Am I going to contribute to some compiler? Well, Simon, among the rest of the GHC community, were very welcoming and really helped me to sort of get into that. And then so what is that, 8 months in, something like that, I made my first commit to GHC, which really was adding extra support for kinds in template Haskell. And so then that started a long collaboration. Simon and I continue to collaborate. We have weekly calls discussing GHC we've had quite a bit of fun together. From there, I then, a couple of years later, was able to get type and type merged into GHC. So this is really sort of deep in. Those of you who are learning Haskell now may not know of type and type because it's since been deprecated because the features have sort of migrated elsewhere in the extension ecosystem. Then there was this other stretch of time, this is sort of in the middle here, more Haskell contributions, more fun things. I eventually became the initial chair of the Haskell Foundation, as Ning said a few minutes ago. And then sometime after that, something happened. So at the same time, I was thinking, oh, it would be nice to sort of experience something a little bit different. And then right around then, something's supposed to happen here. There we go. Right around there, then these three men came and kidnapped me. So this is Ron and Leo and Stephen, who are, I don't know if they're in the room, but they're definitely all at ICFP this week. We started to talk a little bit about Jane Street. That sounded like an interesting idea and a fun new opportunity. So indeed, I taught myself OCaml in 2022 and then joined Jane Street right after that. And then now we are in the process of rolling out OxCaml, which is sort of a version of OCaml with a bunch of extensions. So I'm sort of playing the same game over again, right? Take some language, go in, make some changes to it, having a lot of fun doing that. And so with this context, the reason I'm saying all of this is how I feel like I do have something that I might be able to say about both Haskell and OCaml. So maybe sort of 10 years in there of pretty intensive Haskell work, and now 3 years of pretty intensive OCaml work. Okay, so with all of this, I have some opinions. Now, here we are. Everyone has traveled here to Singapore, and we do that because we love these languages, and we love functional programming. And so that makes us all a large circle of friends. So I'm going to share some opinions among friends. And so that means that maybe you disagree with me, and that's great, and let's have a conversation about that. So, of course, you will have your own opinions, and that's the beauty of these conversations, is that we can exchange these ideas, see where maybe these languages should evolve to. Okay, so again, the big insight is that these languages have a lot to learn from each other. But that's overbroad. We can't really action that very well. So let's go to a minor, probably wrong insight. So here I have this graph of whether a language is sort of more implicit or explicit at runtime, more implicit or explicit at compile time. And it turns out that the two languages are quite different when plotted here. So this is all sort of a rough estimate, but this is about how I would position the languages. So Haskell is down at the bottom. It's implicit at runtime. What I mean by that is that when you look at a Haskell program, it can be a little bit hard to tell actually what it's doing and when it's doing it. On the other hand, it's quite explicit at compile time. We know what side effects are going to happen. We know often what the types are. People write type signatures in Haskell programs, even though they can be inferred, but people tend to write them anyway. In OCaml, on the other hand, OCaml is pretty explicit at runtime. We often know exactly how an OCaml program is going to evaluate. There is an optimizer in OCaml, so that muddies the waters a little bit, but the optimizer in OCaml does quite a bit less than the optimizer in GHC. Oh, I should also say, I'm going to talk about Haskell. For the most part, I'm really just referring to GHC. Sorry, Leonard. But that's sort of the implementation of Haskell that I'm thinking about. So here in OCaml, I say OCaml is more explicit at runtime. Again, we have a better idea of how an OCaml program is going to run, and yet it's somewhat more implicit at compile time. As we'll see, there's a sort of more type inference going on in OCaml than Haskell has, and as a matter of course, OCaml programmers tend not to write type signatures as they're writing functions. OCaml programmers do write interface files. That's sort of off somewhere else. But when you're actually writing the implementations of your functions, there's usually no types around, which for me, coming from Haskell, was really quite a surprise and disorienting, that I'd be looking at functions and like, what are the types of these things? I don't want to have to do type inference. That is more of a cultural thing. You can write type signatures on OCaml functions, but no one ever does. Okay, Andre does. Andre does. You can do very close. It's embedded. You say let f colon type equals. I so I can't hear you, unfortunately. So just for the purposes of sort of the recording, I'll try to summarize what Ron said, which is that because the type system in OCaml is simpler than it is in Haskell, we can sort of get away with doing more inference and writing fewer types. There is truth in that. I don't totally disagree. I will say, as a reader of OCaml programs, it would be nice to have more types. But the flip side of that is that we can have, if we have good tooling support, maybe that sort of closes the gap a little bit. I see a hand up toward the back.
So, I'm just trying to establish the parameters of what you're talking about. When you say that OCaml programmers tend to not write types, is that OCaml programmers at Jane Street tend to not write types, or is it OCaml programmers in general, just like Haskell programmers in general tend to write types? The two are closely the same.
So I think the latest count that I saw is that Jane Street has 80 million lines of OCaml code. I don't know how many million lines there are in total of OCaml code, so you can you can guess what the percentage is there. But code I have seen both within and outside of Jane Street has not had the type annotations, but I admittedly have less experience with the OCaml open source world, and so maybe I have blind spots there. That's a good point. Yes?
When you were talking about explicit versus implicit, you referred to laziness in Haskell and strictness in OCaml. Did you have anything else in mind, or just that?
The other thing that I have in mind is the way that type classes operate in Haskell, in that you can have a function that is parameterized by a type class, and actually what it does at runtime might depend on what type class, what type is inferred for that function. And so this means that sometimes it's hard to tell what a function is doing unless you've done type inference already. So it's not just laziness.
Ooh, okay.
Okay, so just, so that there's more reasons to throw tomatoes at me, I've put a couple of other languages up here. I'm not really going to talk about that at all. Okay, so let's talk about runtime. So that's a good segue from Phil. So here we have some differences between the two languages, right? Haskell is lazy, OCaml is strict. Then this middle one, in some sense, these features are quite different, type classes and modules, but they both serve the same role in the overall language design, in that they allow us to sort of do abstractions over types with complex interfaces. So we'll talk a little bit about that. And then Haskell has a very, very powerful optimizer, and this is needed in the Haskell world because of the way that it interacts with type classes and with monads. We really do have a strong need for a big optimizer. OCaml has less of a need for this, and so the optimizer is considerably less powerful. But again, that means that we have more predictable performance. Again, there is an optimizer in OCaml. It's just not quite as far-reaching as GHC's.
It could mean that there's a lot of performance on the table.
Yes,
waiting for somebody to do that.
Yeah, that is true. It is what we're saying. I meant to make this point earlier on about sort of my little timeline thing. So even with my 3 years of experience at Jane Street, sort of when I think about, if I close my eyes and had to choose, what language am I going to write my next project in? It would still be Haskell. My heart is still there. That said, I think because of the predictability of performance of OCaml programs, OCaml is unquestionably the right choice between these two languages, and probably among all other languages too, for Jane Street. So I'm a huge supporter of that choice at Jane Street. Although there is something aesthetically sort of more pleasing about Haskell. I haven't been able to escape that. Okay, so let's look at, so we'll explore a bunch of examples through this talk of code. So here, I conveniently, and the other thing I should say, there's going to be a convention through this talk. Haskell is on that side, OCaml is going to be on this side. Yeah, I should have placed you and Ron in the right corners. So here, luckily, I could just put this at the top because this works in both languages. But the question is, so I have a bunch of polygons. I want to figure out in these polygons where the triangles are so that I can render them, right? So we're in some kind of 3D rendering engine. Well, in Haskell, I haven't even said what the types are here, but it's a little bit hard to tell exactly what's going on. When will each polygon get triangulated, right? So I have a bunch of polygons. Is it going to be sort of one at a time? Is it going to be all up front? What's my sort of performance characteristics of this? Do I start rendering before finishing the triangulation? That's really going to depend a lot on laziness, right? If I have a lazy structure and if I have good consumers, a good consumer in render, then we're going to interleave, at runtime, we're going to interleave the rendering and the triangulation. Maybe that's good, maybe that's bad. And does the result depend on type inference? That I haven't written out types for these functions, but if I just look at this little piece of code, maybe render is an overloaded function. Maybe triangulate is an overloaded function, and the way that these operate is going to depend on type inference in some way that's hard to discern from the code. I don't have these problems in OCaml. In OCaml, I'm going to triangulate those polygons and then render the result, right? This and furthermore, unless I'm in some slightly less common, higher order setting, I know what render means and I know what triangulate means. There's not going to be this implicit type class overloading that Haskell has. So it's just a little bit simpler, but maybe slower. Again, unless someone has gone in and performance tuned these functions, one possibility for slower is maybe my viewport doesn't include some of the polygons. And so if I'm lazy, we would figure out that I never need those polygons triangulated, that we don't have to do some work. Whereas we're going to do all of that triangulation in OCaml. Again, there are ways in OCaml to make this fast again, but it takes a little bit more care from the programmer. Yes, Ron?
Instinct about graphics programming is that the version of viewport limitation that you get in Haskell will be bad. Like that the implicit thing laziness will not do what you want. And if you actually want something performance, you need really direct control and explicit understanding of how you decide what to compute and what not to compute. So the maybe I feel like if we're talking about writing a graphics engine, I feel like the rely on implicit laziness in the language is maybe not going to work.
I agree with that. This was a 3-word example. I mean, but I wanted to get. I'm not saying it scales to reality, but I think it does serve to sort of show that sometimes strictness can be bad, because it does mean that sometimes you compute results that you don't necessarily need. Okay, so having lived in these two worlds, this lazy and this strict world, what do I think of it? I think laziness is a little confusing. I don't think that I'm the first person to say that. There's a talk somewhere out there about a hair shirt on this point. But laziness is kind of good, and especially when it is explicit. So if I am opting into laziness and I know what I'm thinking about when I make something lazy, I think that's quite powerful. And so I would like it to be explicit, except the forcing bit. It's really nice in Haskell if I have a lazy value and I just try to case match on it, that I don't have to explicitly force it. So where should we go with this? I think it would be great in Haskell. I've wanted this for quite some time. So in Haskell, we can label fields of data types as strict, but we don't have a label to make them lazy unless you turn on strict data, and then you can label them lazy. But I just want a mode where I have to label every field of every data type. And I shouldn't have to impose this on everyone, right? This is just sort of a warning maybe that I turn on in GHC. But it would be really nice to force me as a programmer to think carefully, do I want this to be lazy or do I want this to be strict? Because it's just too easy to rely on the default. In OCaml, it would be great to have more laziness, because sometimes that's a really nice feature. And so right now in OCaml, I find it a little syntactically heavy. You have to label it lazy when you're building the thing, and then it creates its own type, and then you have to force it explicitly. Maybe there's a better way there. It's not entirely clear that that works out, because it's, one minus to having pervasive laziness is it also means pervasive checking to see if a thing is a thunk. And so there's some careful design work that would have to be done in order to make laziness a little bit more ergonomic in OCaml. Okay, let's get on to another example. So here I have some input. Again, I'm not really saying what the type is. I'm going to filter some predicate P over it and then map some F. And the question I have is, there's an intermediate structure here. Does that get built? Well, in Haskell, probably not, but it's a little bit hard to know, right? I'd need to know what the types are involved. Do we have rewrite rules? That's the citation that's up there, very small. Do we have rewrite rules in effect? And actually in Haskell's, in GHC's standard library, there's this very carefully constructed, good producers and good consumers, and we have to make sure that all of these things chain together well, and it takes quite a bit of work to maintain. But it does mean that we get deforestation a lot of the time. That's what it's called when you don't get the intermediate structure. It's called deforestation. And it is quite powerful, but we have to just make sure that we've done the right map and the right filter, and if you implement your own from scratch, then it probably doesn't participate, so it's a little bit fiddly. And in OCaml, yes, you get an intermediate structure. Again, predictable performance on the right, but maybe not quite what you want. Okay, so what do I think here? This one's really hard. I personally can't seem to come up with a strong opinion on what's better. Do I want a powerful optimizer that means I don't really have to think about performance most of the time, and I just get decent performance out of the box? Or would I rather have something where I can really understand the performance and predict it in advance? And these things sort of play against each other. Again, my sort of, the stance I said earlier still holds. For Jane Street, I think the answer here is pretty clear. But in general, it's a little bit hard to know what I think here.
A Haskell story is pretty good here because you can have inspection testing. So you can add to your test suite that this exactly deforests and fuses.
Yes, absolutely. And then there was another point over here.
So in both Haskell and OCaml, the solution to this, in my mind, is simply don't use list, use sequence. Or, they both sort of boil down to you're probably using the right type, wrong type if you care about materializing intermediate structures or not.
Sure. What if you have arrays? I mean, this sort of the same challenges apply. I saw there was a point in the back, Matthew.
So what if the types told you exactly where there will be an intermediate structure and where there won't? Would you be happy with that?
I'm not sure what you mean by the types telling you.
Well, so there is work where it's a variation on stream on all the stream fusion work that you didn't mention, but which is alternative to the reference that you gave. Where it's the fusion will happen so long as you inline everything, but there's a specific type that will show you it will be a type of buffer, and there you know that there will be copying going on, but otherwise no copying so long as the inlining happens. So you can then ask the compiler you could basically maybe force the compiler to inline, and then you have a guarantee that things are going to be copied, but only where you think they are, because the types are telling you that.
That sounds pretty good to me. Again, to me, I think the key thing is predictability. And so if you're operating in a type where you know that there's never going to be intermediate structures sort of no matter what you do, because you'll get an error if you chain together the wrong functions that would produce an intermediate type, that sounds pretty good. Okay, let's carry on here. And this connects back to Jeff's point, is that you need to check your work. So I think that this site is lovely. I have nothing to do with it. But there's this website, godbolt.org, and it allows you to type in some code, and then you can see the assembly code that's generated by your Haskell or OCaml code. It supports many other languages also. And so it's a great way of just telling what's actually happening under the hood. Okay, let's move on to, that was some runtime stuff. Let's move on to some compile time stuff. So I kept trying to come up with a way of saying like my initial stance here without it being opinionated, but I failed. And that is that OCaml type inference tries harder. So we just get more inference in OCaml, but GHC is more predictable. So like this is sort of the opposite problem that we have in the runtime stuff, is that I find even after a bunch of programming in OCaml, I just find what it accepts and what it doesn't accept to just be harder to anticipate from first principles. Not that there aren't rules. There are rules. It does have principal type inference. We can figure it out in the end. Just like in Haskell, eventually you can figure out exactly where things get forced, even in sort of nested lazy structures. It's just harder. So let's look at a couple of examples here. So this first one is actually, everything is already up on the slide, in that this has a type signature, right? Haskellers will write a type signature on that function, even though it's a pretty simple function and its type can be inferred pretty well. Oh, by the way, I've turned off numeric overloading for this talk. There's no overloaded numbers in Haskell. But that is cultural, right? You can delete the first line. Yes, it is cultural. But the languages are as they are deployed in the world, which includes their culture. Yes?
This to me seems like a quite deep cultural difference, because my immediate thought is, how did you write this function if you didn't even know what type you set out to implement?
Well, you did. You just didn't write it down. Yes. So when I started doing OCaml, that's exactly how I felt. I've become more used to it over time, but I still, the good news is that especially nowadays there are powerful language servers in both languages that allow me, when I look at a function, I'm like, oh, what is this? And I'll just quickly query its type, and then that's just as good as having it in the source code for the most part. Having it in the source code also means that you have it available in review contexts and when it's up on GitHub and sort of in other places. So I still think that having the type written out is a little bit better.
So there clearly is this cultural difference, but I wonder how much of that is just a purely ergonomic thing. In terms of OCaml, you can, in theory, write the type signature there, but it's kind of ugly because it's sort of stuck in the middle. It's really convenient to be able to stick that signature beforehand. Do you think that's the...
Maybe. It could just be an ergonomics thing. So those of you who don't know OCaml will see an example on, here we go. And so we'll see sort of a slightly better example in like 30 seconds. So here, if I write that code in Haskell, well, we say that this should work for any A, and it's not going to work for any A because not every A supports plus, so that doesn't compile. Over in OCaml, on the other hand, so this demonstrates Sam's point, I think, in that here I have this type signature, alpha to alpha, that's how that's pronounced in the OCaml world, and then I have to have this sort of fun. I can't, it's just not quite as smooth looking. But this is perfectly fine in OCaml. And that's because a type variable in OCaml means I just didn't bother to write down this type, but you figure it out for me, compiler. And so add1 will get accepted with this definition. It'll be given the type int arrow int. It's not given the type alpha arrow alpha. That would be bad. But again, this is quite different from the philosophy that exists in Haskell. So in OCaml, we can do better. And if I write for all alpha, OCaml just omits the word for all, but it still has this syntax. Then indeed this will get rejected. Right, and so this extra for all alpha is closer to the Haskell type signature, but this is very rare, at least in my experience in OCaml code. Ron.
So one, I think, important cultural and technical difference that I think is very important when you think about how types show up in the language is signatures, right? Like I think maybe like the single sneakiest best feature of OCaml is that, which some people who are not OCaml programmers think is a bad thing, but I think it turns out to be a great thing, is separate interface files. And people carefully and lovingly create interface files that say at the level of a whole module, like what are the types here and what are the signatures of all the things, and that's like a very good and very ergonomic part of the system. And I think part of the reason why people are not writing the type annotations inside the implementations is there's another place where they are writing them.
Yes, that's a really good point. So in this talk, I'm focusing on sort of the ML files and not the MLI files. But I completely agree with what Ron said, which is that when you have, because in OCaml, you have these separate files that describe the interfaces to your modules. That's the place where the type signatures go. And at first, when I started to do OCaml, I was like, I have to repeat everything, and this is kind of annoying. No, actually, it's great, because it means that I have one place I can look at to understand what is the interface to this thing. Haskell has this somewhat, so unfortunately, I don't have a slide on this, so I'll just sort of do it live a little bit. But Haskell, you can write at the top of a Haskell module, you write down all of the things that you export from that module, and that has some of this flavor. But it doesn't you don't have the types there, so the types now are sort of distributed throughout the module. It becomes sort of harder to navigate, whereas in OCaml, you do just have this separate file, and everything is right there. And there is repetition, and that does take real programmer time as you're working on it. But in the end, I think the ability to read the code is worth that time spent in producing the repetitive code.
I just wanted to point out that the original design of Haskell had the ability to have handwritten interface files. The .hi files could be written by hand.
Ah, that is news to me. I did not know that. Thank you.
I think one of the reasons that we also don't write types at the structure level is that in writing type variables, there's actually 3 different syntaxes we can use. And there's not actually one most general syntax that we can use. And there's like subtle cases where they do work and they don't work. And it's not clear to users why.
Yes, that's true. So instead of saying tick a dot here, I could have said type a dot, and that means something subtly different. That's not something I'm going to really explore in this talk, but that is true that there's a bunch of different ways of doing this, and they're all just slightly different from each other and a little confusing. Okay, let's move on. So let's look at some G80T inference. So over here on both sides, I declare type T and a constructor that constrains the argument type of T. So over in Haskell, that's going to be rejected. We don't know what type to give to F. We can't tell, should it go from TA to int, or should it go from tbool to int, or something like that. Over in OCaml, sure, we can accept that. Again, this sort of goes back to my type inference just tries a little bit harder. And so here we can infer what type F has and say that it just goes from bool to t. It makes that decision. It does have principal types, and that's it's slightly subtle to. What was that? Well, this particular definition of F doesn't support that because it doesn't have a locally abstract type A. We could talk more about that later. Yeah. This still is this is not my favorite area of OCaml type inference. Okay, so what if we had 2 different constructors? So now it's tbool or tint. Well, still on the Haskell side, we're not going to know how to deal with that. And then now over in the OCaml side, once again, now this has become too complicated for type inference to deal with over in OCaml. So the way to get a G80T pattern match to work on OCaml is to use this extra type construct. But let's first look over at the Haskell side. So on the Haskell side here, now I've given a partial type signature to say that I definitely want this to take a TA. It's not going to be a tbool or a tint, but a TA. But the result, I'm just not going to say what that is. So this is a less used feature in Haskell to be able to just sort of leave out part of a type. It's actually quite a common thing to do in OCaml, to just give part of a type. And you would think, oh, well, this clearly returns an int. But Haskell says no. And that's because maybe it doesn't return an int, maybe it returns some type family that operates on A, and it is true that returning int here would not be principal. But most of the time, we probably just want this to return an int. And so over in OCaml land, it indeed just returns an int. Well, in OCaml it is, because OCaml doesn't have type families. So this goes back to, it's a slightly weaker type language, so we can get a little bit more from it. And so in answer to sort of Simon's point earlier, is like, how could we have inferred bool t arrow int on the previous slide? Well, the only way to sort of do proper GADT pattern matching is to have one of these type A declarations, to say, here I have the type that's going to be discerned. And if you don't write the type A, then you don't get a proper GADT pattern match, so it was still principal. It's a little different than Haskell. Okay. What was that? That does not need a quote, no. This goes back to Alistair's point of there's multiple different ways of doing things, and they're all slightly different and confusing. Okay, over here in Haskell, we can finally accept this if we label the return type as int, and now we've said enough about this GADT pattern match in order to accept. Okay, so let's talk about type classes a little bit. So here in Haskell, I have a function, and obviously I don't know what action 1 and action 2 do. But what also I find slightly alarming is that I don't even know what the invisible semicolon does. So what no one in the room sees is that there is a semicolon right here between the two lines, and because the do inserts that semicolon for us. But I don't know what monad this is operating in. And so different monads have very different behavior about how they string together one line to the next. And so here I'm going to have to use type inference, and maybe action 1 works over any monad, but action 2 works only over a specific monad, so then I have to look at action 2's type, figure out what monad it works in, and that must be the monad for the whole do. And this causes a challenge for readers of this code. And so that's why I often, when I have multiple monads near each other in Haskell code, and I write do, I'll just have a little comment saying which monad I'm using. And actually, Haskell has recently gotten, or not so recently, but qualified do, which allows you to sort of specify a little bit more directly what monad you're operating in. And so this can be sort of a slightly unpleasant part about type class inference. Let's look at modules for a sec. So here I can have a module that looks like this. And modules are a really powerful mechanism in OCaml because I can take different interfaces and combine them in different ways and then build up large, complex interfaces by mixing others together. The minus is that when I actually use this, figuring out what is exported is quite a challenge. And so there's tooling to help with this, but in practice, sometimes you end up jumping from MLI file to MLI file to MLI file, trying to figure out what's going on. And I'm seeing sort of knowledgeable nods from some of my Jane Street colleagues on this point. And so again, with a language server, we can do a lot better, and in fact do that, and so we rely on that. But modules are powerful, but with power comes oof. So let's see. We should get, okay. So what about the comparison between these two? So as I said earlier, that both of these features give us powerful ways of abstracting over types with complex interfaces. And so should we have type classes or should we have modules? Well, I think we should have both. And what's fun is that both language communities also seem to think that we should have both. Way back in 2019, I proposed local modules for Haskell, which admittedly is not modules in the full glory that OCaml has, but rather is more of a sort of a namespace mechanism. But it would really quite allow us to organize Haskell code a lot more than it is now. And then also, a number of colleagues put together a proposal for modular implicits in 2015 as a feature for ad hoc polymorphism in OCaml. So this is not quite type classes, but it gets much of the way there. And so what do I think that we should be doing as communities? Well, in Haskell, it would be really nice to have better namespace control. So that local modules proposal, it sort of ran a little bit of ground on technical issues, and I'll admit I sort of ran out of steam trying to sort of push that one through after sort of the 10th random small technical issue. The broad idea was great, but the last 2% was really a struggle. And so I don't really think that Haskell needs proper modules in the way that OCaml has with sort of a functor discipline. I just don't think it's needed. I think it's a solution to a non-problem that in Haskell. It might be nice, but it would add a lot of complication.
But it's a solution. Why is it a solution to a non-problem if in OCaml it's a solution to a problem?
So hold that thought. So in OCaml, I think that we should add type classes called modular implicits, but without the global coherence property that Haskell has. That global coherence property in Haskell is very anti-modular. And that would just sort of really go against the grain of OCaml. But the modular implicits proposal sort of happily keeps that property away. So right now, there is active work by Didier Remy and Samuel Vivien on working on modular explicits, which is a precursor to modular implicits. So this is actually happening, and we have the little OxCaml logo because we expect this to become part of OxCaml at some point. Maybe it'll also become part of OCaml at a similar time frame. I do believe the OCaml community has good support here. And then this is more of a direct answer to Simon's question, which is OCaml does not have support for higher-kinded types. And this means that, but sometimes we want to be able to abstract over something with higher kinds. So we might want to talk about a collection in general, where we leave the element type of the collection sort of polymorphic, but we want to be able to talk about all different collections that are polymorphic. The only way to do that in OCaml is to use the module mechanism. And so, because Haskell has higher kinds, Haskell has much less of a need for modules, for sort of the functor-based module system that OCaml has. It remains to be seen once we have higher kinded types, and once we have modular implicits, then how much do we end up using the module system versus these other features? I think that there's some experimentation to be done and some more understanding to be found there. Let me just say, so this is Kuba Bakursky, who actually implemented higher kind of types as an intern project at Jane Street last year. So that has not yet been merged, but I hope it will be soon.
Perhaps I can just add a comment here. I think the whole higher kind of type thing, it kind of slipped into Haskell fairly early. It was Mark Jones, who was largely in support of then we can have type classes that abstract over monads. I think that was a sort of killer app initially. But it seems to be that feature alone has given birth to an enormous amount of creativity in Haskell space. You can't talk about categories and monoids and lenses and bifunctors without high kind of type levels. It's amazing how much you can do when you have that one feature. And it turns out that unlike other type system features like indicativity, it's really easy to do, except you do have subtyping, which you do.
Well, we do have subtyping, but the problem is more that we have subkinding.
Yeah.
We could talk more about that offline, but.
Anyway, this thing is that people often say, what's distinctive about Haskell type classes? For me, high-kinded type, that's a huge deal.
Yeah, I agree, and so it's one thing that I'm looking forward to seeing how once we have higher kind of types in OCaml, how does that change our library structure? There's a point over here.
What's the use of adding higher kinded types when you can't talk about their behavior? Like, so your point was, we want to reason about some form of collection that's parameterized, but that's not very useful in itself if you can't talk about R, but it also has a map function as well. And so really you want both to talk about some form of parameterization of the type and its behavior, which is what you get with higher kind of types and type classes.
Yes, I agree. Okay. Yes. Yes, or modules, which is why right now they're tied into modules.
I guess my question is, we are almost there with modular explicits, so why do we need high-kinded types if we're just going to pass behavior around explicits?
Oh, because we still need to be able to sort of talk about the higher kinded types. I mean, as in, I want to be able to talk about a collection just in sort of in abstract terms, and then that requires some amount of abstraction over higher kinded things. We can maybe talk more later. Okay.
The slide says Haskell, but not proper modules. But I thought we had Backpack, and no one uses it. So we do have proper modules, right?
So maybe I phrased it more sort of provocatively than I needed to. When I say proper modules, I really mean sort of OCaml style functors, which are functions that take in a module and produce another module. So one strange thing is that both Haskellers and OCamlers talk about functors, but they're totally different concepts. That's true. That's true. Interestingly, a project that Jane Street is under at the moment is essentially taking Backpack and porting it over to OCaml. So this is so in OCaml world, this is called parameterized libraries, and it is more ergonomic than some uses of functors. I don't have slides on this, so I don't want to go sort of too deep into that right now. But interestingly, we're taking very similar ideas to Backpack and moving it over into OCaml. Okay. Okay. So this is a particularly sort of favorite subject of mine to sort of think about purity. Even after 3 years of programming OCaml, I continue to be surprised by mutation. So that said, I want to think a little bit about Haskell and about purity in Haskell. So in the GHC compiler, we have this operation called zonking. How many people here know what zonking is? Okay, just a handful. I'm surprised to see sort of more of an OCaml person raising your hand about zonking. This is very simplified. Don't try searching GHC's code for this. You will not see it. But in GHC's internal representation for types, we have the possibility that a type is a unification variable, right? I'm in the middle of type inference. I don't know whether something is going to be an int or not, and so maybe eventually I learn that it's an int, and then I can fill in this IOREF. IOREF is how Haskell spells what OCaml just calls ref. And so here it starts out empty, and then might get filled in with something like int. But then the problem is that now to be able to see that a type is really an int under the hood requires that I operate in a monad. Whereas so many of the algorithms that GHC has really don't care about the difference between the type variable alpha and the int stored inside of it. And so it means that GHC has to be quite careful about this operation called zonking. Oh, zonking is when we take the alpha, take the unification variable, and replace it in a structure with int. It's really just applying a substitution. But it's this idea that as we've accumulated the substitution, that instead of being stored in some kind of substitution structure, it's just stored in memory by using these mutable references. But it's the act of essentially applying that substitution. So because we have to be careful about this, there's a lot of time that Simon and I and others have spent trying to figure out exactly when do we zonk, how do we want to zonk, and then we had to come up with the purely well-kinded type invariant and such, because sometimes we're in a pure context and we don't have access to zonking, and it's just all a little bit uncomfortable. And so it's kind of annoying. But not having purity is just worse. I will keep the purity and keep the annoyance, as opposed to over in OCaml, it's really quite hard sometimes. When I go into a new code base and I see some function operating over some large structure, is it mutating that structure? Does it matter whether I apply something before or after that other operation? I really don't know, because I can't tell the difference between side-affecting operations and pure ones. And so this I find is sort of a challenge in OCaml programming. But maybe with some of the ideas that we're coming up with in OxCaml, maybe we're going to improve on this. So I gave a couple of sort of mini talks during the week out at the Jane Street booth. sort of showing how new features that we're adding to OxCaml control purity and allow us to have this notion of referential transparency. That's really what I'm after, is referential transparency in OCaml. And this is still very early days for this feature, although the compiler parts have been implemented. There's a lot of library work to do, because now we have to go in and essentially label all the pure functions as being pure. And so we haven't done that yet. So you can't even add two numbers together purely in OCaml yet, even though the compiler sort of understands this idea. But there might be sort of an interesting middle ground here that we can sort of navigate. And I'll be really curious to see in a couple of years, as we continue to develop this feature out, how this weighs against purity as it exists in Haskell. Okay. A few maybe smaller points about scope in the two languages, because this is another area, and this is an area where my own opinion evolved after programming in OCaml for a bit. Okay, so this is actually, this first example did not evolve. So here I have a sort of a terrible way of computing the next. If I have two numbers in the Fibonacci sequence, I want to compute not quite the next two numbers, but sort of the next pair of numbers, sort of move one up. And this computation does it. This is very silly code. But over in OCaml, this just kind of makes sense. I can shadow N2 and I can shadow N1 and everything works. It's fine. If I write this in Haskell, I get a horrible loop. Right? And that's because every Haskell let definition is recursive by default. In OCaml, if I want a recursive function, I have to explicitly say, please make this recursive. And so OCaml, we just get nice shadowing. Things are good. I think recursion should be explicit. This was true. I thought this some time ago. I'm not the only person to think this. So there was a proposal from, when was this? 2021, to add, again, optionally, the ability in Haskell to sort of mark things as needing explicit recursion. And I was a fan of it back then, again, before Jane Street. There's a question in the back.
Oleg Kislyak has a really fun identity monad trick, because if you use do notation in the identity monad, then you can have non-recursive let bindings.
Yes, that's true. So we can use the identity monad to avoid this problem, because in monadic notation, that is not recursive by default. But that's a bit heavy, I think, to get around to sort of a scoping thing.
But it is, the recursion you showed is explicit because you're shadowing, right? So like you're calling N1 again. You've chosen to shadow a variable that's bound by a let, and so because you've chosen to call that, isn't it going to be explicitly recursive?
In OCaml?
No, in Haskell.
Well, actually, I mean, going back to the, where has it gone? Here it is. I mean, this Haskell code, both the original N1 and N2 never get used. Those are unused variables. See, it is confusing. That's a good point. Yeah. So in OCaml supports equi-recursive types, which is a bit strange. Also, that's not something I have a slide on. But yes, that's a good point. No, in Haskell we don't have that. Oh, that's not what you're talking about. You're talking about the fact that in a type declaration in OCaml you get recursion by default. Oh, that one I'm not sure about. Probably better not to have that on by default. But many types are recursive, but it is awkward, especially when every type is just named T. Yes, but yes, that's true. So types. So in OCaml, normal variables are not recursive by default. Types are recursive by default. Modules are not recursive by default. And so there's keywords. There's a rec keyword to make them recursive and a non-rec keyword to countermand the recursion on types. Probably this could be a little cleaner. Okay, where were we? Over here. Okay. So here's another difference between the language, and this is the one that I said sort of evolved as I programmed in OCaml. So here I have a case of a function f that when I initially defined it, I wanted to have some accumulating parameter so that it can be more efficient, say. But then the version of f that I want to expose, we don't want to expose that accumulating parameter. So here, I'm just going to define a new f that calls that first one up there. Of course, that makes no sense at all in Haskell, and that's because Haskell does this sort of global inference to try to figure out what order your definition should be in. In OCaml, on the other hand, this is just fine. Things just work from the top down. And at first, I thought, this is kind of annoying to have to always work in top-down in OCaml. But having seen a number of different ways that this has played out, I think OCaml got this one right. I think bindings should be ordered. In Haskell, it's not just the explicit recursion, but by having bindings be ordered, it allows us to control our namespace just a lot better. So let's see another example of why we might want this. So here in Haskell, if I import data.set and I import data.map and then I talk about empty, I get an error because empty is ambiguous. Do I mean data.map's empty or data.set's empty? Over in OCaml land, I can open set.makeInt. Let's not get into why there's like a functor application here right now. But I can do that for set and map, and if I talk about empty, well, I just mean map's empty because that's the one that's most recently in scope. Maybe I meant set's empty, in which case I get a type error. But this also means that if I have, say if I have some module that exposes something that I just don't care about, I can just shadow it later on, and it's just so much easier to program with. Ron has a point. So I'm saying something nice about OCaml. Ron, you usually react when I say something negative about OCaml.
So, I mean, I think the shadowing is like a complicated example. I think it's good to have shadowing, but like it's a little messy, and I can see why people wouldn't like the example on the right fully, right? Because it's like let equals empty. It's like a little, even if you see the ordering, it's kind of a little bit of a spooky action at a distance and stuff. But like I think there's actually a much stronger reason to want bindings to be ordered because it makes it easier to reason about your code, right? The reason for recursion to be explicit is because recursion is harder to think about. The reason to have ordering is because you're just reading things in definition order. You know, like that first one on the top of the file, what does it depend on? Nothing else in the file. The next one I read, what does it depend on? Only the things ahead of it. It's like a constraint that makes the code easier to reason about. And I think that's the primary reason why I think ordering is important. I like the namespace construction thing is useful, but I think the ordering, the reasoning thing is primary from my perspective.
Sure, I agree with that. There's a comment, right? Gergo.
So, because you said at the beginning that you're saying opinions and we should also say opinions. So this is just like, I want to say my opinion on this, which is that I think import shadowing, so when is the Goldilocks point in this design space. So basically, I think if you define empty in the left-hand side and then in the same module and then use it, it should be clear that you mean the empty that comes from the module that you're defining. I don't like the one on the right where imports are ordered. So I think, so you should think of all your imports as a set, but then the module you're defining is one scope deeper. And there is actually, as you know, but maybe not everyone knows, there is actually an open proposal for this that unfortunately I had to abandon for other reasons. But yeah, there is. It seems like there is community agreement from the Haskell side that that's what we want, because that proposal had gotten really good feed or uptake from community.
So that, I mean, I see what you're saying. The reason I still think ordering is good, at least for sort of this scope thing, I agree with Ron's point that there's also a reasoning principle, but sometimes you just have a module that exports a function that you just don't want and don't care about, and then because of that you end up with an ambiguity problem. And there's sort of, I mean, yeah, you can say hiding, but in practice I find that just kind of painful, whereas that pain doesn't arise in OCaml. It's just sort of a better world. In
but
that
you
way.
get a different pain if your modules would have exported at the same type, because then you're not going to get type error. You're just silently going to pick the second one.
Yeah. No, there's not one right answer here necessarily. I see. While the mic is in the back, let's.
There's another thing is that here the two are basically like imports just side by side, but often one of them is going to be much closer to your use point. Like you can have a local open, and the fact that it works the same if you have like some opens at the top and some opens like inside your function, even inside your function body, at whether like it's only the order matters, not the, are they like the imports that you do at the top of your module versus that. So I think that in OCaml it's quite easy to think about, because it's the same thing. Like, it's just you have the list of opens beforehand, not you have a bunch of open at the top level of your. Sometimes they can be top level, but like at different points in your file. So you can have a local-ish thing where.
So if I can just sort of jump in. So I think this is fantastic. This is exactly what I wanted to happen. And now maybe there's a conversation that happens during the break, because I feel like a lot of people are going to have opinions on this point.
Yeah, work?
Yes, I find that kind of annoying.
Yeah, so I was supposed to say that, but like actually I think you got the point to quite extent. Like, if I have an open statement command, what would you call it, somewhere in the middle of my file, I don't want to have to look for it. If it happens just to shadow some name that I wanted to use from the top of the file, which was imported originally on the top of the file, where I would look for imports, right? And now I have to just scan and look for all opens on the way to find like where it's actually went wrong.
Yes.
If it's local, then I could agree shadowing makes sense. That's the perfect use of it. Maybe I would just use a different keyword then, but I think like a mixture of those two would work. And also in Haskell, I would just like to remind that in such a case, in the case, okay, maybe it was the previous example, you also have the where keyword, which...
We're going to get there.
Okay.
So I think in the interest of time, I'm going to move us forward, but I think we're already creating this nice conversation about sort of these two different language designs. So here's another example of kind of the same idea, that in OCaml we can actually just shadow constructors and use them, and this is just kind of nice, because it means that if there's a constructor, again, that maybe is imported that I don't really want, I can sort of cover it up. And this is convenient. Sometimes actually the shadowing is intentional, and I take something that might be useful but dangerous or somehow bad, and I shadow it with something that's useless on purpose, so that programmers can't access the bad thing, and this can be quite nice. Okay, I do want to move past just sort of the shadowing thing. I see there's some hands up. Is it just about shadowing? I think we'll move on. But let's have this conversation during the break. This is like, I'm very excited to see people's excitement on this. Okay, one slight variation on this on the OCaml side is that OCaml actually supports type-directed name resolution. And so if I have a type annotation on this F, even though the bottom A and B shadow the top A and B, I can still access them if I have a type annotation. And so there's no way to do this in Haskell, because over here we can't have multiple different names introduced that are the same, but here it's fine. This, admittedly, I understand why GHC doesn't have this. It would be very hard to integrate this into the structure of GHC as it is. Although, interestingly, there is no way to live without interleaved type checking and name resolution in OCaml because of the way that the module system works. So the OCaml compiler must interleave the name resolution and type checking. So it makes something like this possible to consider. Okay, a bunch of small syntax things. I think there's probably going to be lots of opinions here. I'm just going to try to plow through. So we have camel case and snake case. I'm actually not going to stand with an opinion between these two, but I think we should use both. So those of you who have, maybe some of you have programmed in GHC. GHC has this wonderful naming convention where local things are snake case and exported things are camel case. This is really nice because it allows me to look at a function and quickly tell, should I be thinking of this as like, a polished exported thing or just sort of a local, maybe dirty thing? And it just makes it so much easier to read and understand the code. Haskell has where, and OCaml has let. So let me give an example of this. So I might have a function in Haskell that has some important stuff and then some fiddly little details. This is lovely. It means that at the top I can just see exactly what I want to see, and then if there's a bunch of supporting details that need to be there because it's a real program, I can write those, but they're down below, out of the way. And it's something that I really miss in OCaml. OCaml, sometimes you have a function, and the first 20 lines of the function are just sort of throat clearing and getting rid of, sort of setting up auxiliary structures before getting to the interesting bit. And so Haskell can tend to avoid this. So I still really miss where, and I think OCaml should get it. But only once we have purity. If we had where and there were side effects, then what order do the side effects happen in? That's just really awfully confusing. If we're working in sort of the pure subset of OCaml and we can track that, then having things sort of appear a little bit out of order in this way makes a lot of sense. And note, this doesn't require laziness, right? It just requires purity. No. The question was, will I touch on point-free style? And no, I'm not really going to get into that. Okay, indentation sensitive versus white space versus white space agnostic. I don't know. I go back and forth on this. Both are kind of annoying, right? Like, we've all spent a lot of time, like, with, in a Haskell, or Haskell programmers have all spent time, oh, something just doesn't work, and then you don't know why, and you're like, oh, I just need to add another space here. That's kind of sad. On the other side, in OCaml, there's a lot of keywords, and they're kind of annoying. I don't know. So Haskell has, I count 5 namespaces for modules, variables, constructors, types, and type variables. Some of these are uppercase namespaces, and some of these are lowercase, so you can divide that up a different way if you want to. OCaml has 11 namespaces that I could find, where you can define the same name, although some of these are capitalized, some of these are lowercase, and then some are oddly both. Module types can be both uppercase or lowercase. Type variables can be uppercase. No one ever does that. So this is just kind of a mess. I think both of these are bad. Let's just have one namespace. It means that names have to be a little bit longer. Maybe 2, so one are capitalized and one's lowercase. I'm okay with that. I think going beyond that is just confusing because it means now every time I talk about something, I have to specify what namespace thing I'm talking about. So maybe no one likes that idea, but I find the divided namespaces to be really quite annoying. Okay, talk a little bit about implementation. So OCaml is just so much faster than GHC. So the OCaml compiler builds from scratch in under 5 minutes, and that's like the production-ready one. The development version that I usually use takes about a minute, and that's for building the Bootstrap compiler and then building the stage 1 compiler and the stage 2 compiler and all of the libraries. It's nice. GHC, the last time I tried, it took, I think, 25 minutes. Often it said, oh, well, that's the optimizer working. Even with the optimizer turned off, it takes a lot of time to compile Haskell code. So I think GHC has some catching up to do here. On the other hand, GHC has this typed intermediate language, which provides this beautiful safety net of adding new features to the language, and where we can know that that the feature is sound if it can desugar down into this typed intermediate language. So that is really quite nice. The flip side is that's part of what keeps GHC a little bit slow, and it also, I think, makes more of a challenge in developing features. So there's sort of a cost-benefit trade-off in that every time we add a new thing to GHC, we sort of have to prove that it's type sound, whereas in OCaml, we can just kind of add it and hope. And so maybe sometimes that's the better choice. Another big difference in the implementation is things like this. So GHC is completely covered with these notes that give overview to different subsystems. And it makes GHC much easier to work in and is a really nice thing. And so I have now snuck a couple of these into the OCaml compiler. If you look in the OCaml, there's 1 or 2 in the upstream compiler. I think there's a few more in Jane Street's branch, but expect more of this in the OCaml compiler as I keep working on it, because these are nice. Quick comments about the community. So one might think, oh, these are, how is the community different? The communities are really quite similar. Both are really welcoming. I was in particular worried coming into OCaml. Was like, oh, here's this Haskeller coming in. What's going to happen? And I didn't feel that way at all. The OCaml community has been very welcoming, and I just find a good collaborative spirit in both. One thing I've enjoyed sort of piloting is in both communities, I've helped form sort of a proposals process by which the community can contribute and build things, build new features into the language. Anyway, I just wanted to sort of dispel any thoughts, oh, those people over there, they're not very nice. I think that that's not true in either direction. I'll talk a little bit about the funding models of the two communities. So both places now have foundations. There's the Haskell Foundation and the OCaml Foundation, both with a bunch of sponsors on both sides. So that's great, right? We have communal places where funding can be drawn into and then dispersed from to develop new features and support the languages. They're a little different in structure, right? So the Haskell Foundation has a full-time paid executive director. That's, at some point, there we go. That's Jose Calderon at the moment. And so his full-time job is thinking about ways to support the Haskell community. The OCaml Software Foundation is a volunteer organization currently directed by Gabriel Scherer, who also puts in a lot of time in thinking about the OCaml community. But this is kind of a difference. It's still sort of early days in some sense to know what's the more sustainable thing going forward. But I just sort of wanted to highlight that there's more than one way to do this. So there is a really big difference between these two communities in that there's no escaping the fact that Jane Street is a big supporter of the OCaml community financially and in other ways by coming to conferences such as this one. And there is no equivalent. There are a number of companies that are players in the Haskell world, but no company with prominence like Jane Street's. Jane Street does this because it's good for Jane Street. It's also good for the community. But we don't do it just out of like benevolence. Right? We do it because we reap the benefits of doing it, and we get to be involved in the community, and we get to help others build things such as multi-core OCaml, which mostly happened outside of Jane Street's walls. And so there's good reasons to do it. I would be very excited to see a company come in and try to fill that role in the Haskell community. I think that for Haskell to continue to thrive, we need sort of more of this. So if you work for a company that uses a lot of Haskell, think about maybe upping your contribution. Right? There's a good template for this, and a good Jane Street I think can show how this can be done. I would love to talk to people about how that works for Jane Street. I'm going to make a shameless plug. This is about another way in which Jane Street is sort of showing its commitment to both of these communities in that we are hosting a Haskell hackathon in February. So this is going to be sort of a North American equivalent of Zurich Hack that the Haskell Foundation is organizing, Jane Street is hosting, so you can find information on the Haskell Foundation website about this. But this is yes, it is at Jane Street, but this is a Haskell event that I'm looking forward to attending.
Will all the participants be kidnapped?
Only some will be kidnapped. Okay, so I want to end with a controversial proposal, right? This has been all about creating conversations between the communities, and some of these conversations have already started, which I'm super excited by. So one thing that I've been aware of as having some amount of organizational ear in both communities is that the Haskell Symposium and the ML Workshop are sometimes looking for more content, so maybe they should be combined. So I do have a name up here. That's just sort of a name I came up with as part of this talk. But wouldn't it be great if instead of having Haskell talking about research ideas about strongly typed functional languages and the ML Workshop talking about other research ideas about strongly typed functional languages, maybe we should just have one room where all of that happens. Now, we still need other rooms where where very Haskell-specific things, or very OCaml-specific things, or very other ML-specific things can happen. And so I think that that should be there too. But the idea that maybe the sort of the higher level, the peer-reviewed research gets put together in one common stream, I wonder how that would work.
So technically, yeah, it isn't the ML workshop, it's the ML family workshop, which maybe is not an appropriate name to satisfy well, what you desire, but that actually does cover a broad range of languages already in its
But not
core.
Haskell.
It does. Haskell is allowed is in scope for the ML family workshop.
The last time I looked at the ML family workshop, it had strict.
Oh.
The ML family workshop says that it's for strongly typed, inferred, functional, and strict languages, which seems to quite loudly say Haskell is not welcome here. Well, then that's maybe something. So I'm not currently on any of the organizing committees that might be able to affect this, but I'd be happy to talk to folks about making it a reality. I see some hands up there. We're sort of out of time right now, so I'm just gonna. I think this might be the last slide. Yes, I want to create new conversations, and there we go. Thanks very much.
You remind me, we have OO Haskell or something a long time ago. I think it's dead, right? I'm not sure anyone remembered. And in Jane Street, can you talk about the object-oriented programming part? What kind of situation you use object-oriented programming that solves the problem better than Haskell, which is a pure functional programming language? Do you have some situations or real-world project?
So you're talking about the object system in OCaml? Sorry.
Yeah.
Generally in Jane Street, we do not use the object system. There's certainly people in the OCaml community that do, but I'm the wrong person to speak about that.
Okay.
Sorry.
I've noticed that Haskell Implementers Workshop is no longer at ICFP, and I really miss that. As someone that's working on the OCaml compiler, it would be nice to have a combined compiler sort of implementers sort of workshop.
That's an interesting idea. So Haskell Implementers Workshop is definitely alive. It was moved to Zurahack this year, where sort of more of the Haskell implementers are sometimes than ICFP. I don't know about the conversation there about whether that's going to stick or not. I'm not aware. But I just wanted you to know that it's not gone. It's just elsewhere. Well, it's not here. But as we continue to think about this, I think that's a good point.
Actually, I have a technical comment, not a question. So you had an example where you show there's GADT programs that are accepted by the OCaml compiler, but not the Haskell, because they use a different type inference algorithm. But if you look at the ambivalent types paper more closely, there are also programs that are accepted by the GHC, but not by the OCaml compiler. So I'm just saying that because we are at the Haskell Symposium, I feel obligated to say that the type inference in GHC is not necessarily weaker than the OCaml, but they have different trade-offs.
Yes, that's a good point. Thank you.
All right, let's thank Richard again for this great talk.
Testing.
of plugins. Please take it away.
All right, thank you. So this is an experience report about a language called Plinth. And so I'll preface it by saying that besides my co-authors here, there are many others, perhaps too many to name individually, who have contributed to or influenced Plinth over time. I think there are actually a few in this room. So Plinth is a DSL for writing smart contracts on Cardano, on the Cardano blockchain. So let me first zoom out and tell you, where Plinth sits in the space of DSLs. So broadly speaking, there are three approaches for DSLs, like standalone DSL, which are new languages. And then there's EDSLs, which should require no further introduction to this room because, in the Haskell community, we talk about EDSLs all the time. And then there's also languages that are subsets of other general purpose languages. This is a relatively less common approach, but it can sometimes work very well, and Plinth is in this category. So here are some examples, and the examples on the right these are all Cardano smart contracts languages. And so that means, when you learn about Plinth, the takeaways are not just from the angle of how, what it's like to implement this language in Haskell, but there's also the aspect of, how this approach compares to other approaches of developing DSLs. So specifically to motivate Plinth even further, what makes it interesting, right? Why you should care. So there are a number of different things. So Plinth reuses a subset of Haskell, like I just said. And this is a relatively less common approach. There's just not that many DSLs that adopt this approach. And so why did we adopt this approach, you might wonder. And second, so the Plinth compiler is implemented as a GHC plugin. So this is also a less common approach within the already less common group of subsets of other languages. Because a more common approach for implementing a compiler for something like Plinth is to develop a standalone compiler with GHC, using GHC as a library. So it will be interesting to see how these, how they compare and what are the trade-offs. And then the Plinth runtime itself is also a sort of fairly interesting piece of Haskell. It's a performance-optimized Haskell implementation of a CEK machine. And it shows that, it's actually fairly performant and the code is actually fairly high level and readable. So it shows that Haskell as a high level, purely functional language is not like inherently inefficient, and you can indeed write very performance optimized code without really sacrificing readability if you spend some effort on it. So I'll speak to these three things in more details. The other three I won't have time to go into, but I will just briefly mention them at the end. So first, a subset of Haskell. What does it mean to say that Plinth reuses a subset of Haskell? So it means that the code is written directly in Haskell syntax, which is unlike EDSLs, which usually needs to invent its own syntax on top of Haskell's, because EDSLs are just a regular Haskell library for manipulating expressions or ASTs. And users will just, need to use whatever types and functions provided by those libraries. And by the way, since this is the Haskell symposium, so when I say EDSL, let's assume that it's embedded in Haskell. And then the code is compiled directly, and this is also so code gets compiled directly by some compiler that is either different from GHC or a modified version of GHC. So this is also unlike EDSLs, which is a regular Haskell library. So all the interesting things, including the compilation of the DSL, happens at Haskell runtime. And this is some of the supported and unsupported features, Haskell features by Plinth. So most of the core FP features are supported, but some of the more advanced features are not. And there are also some semantic differences between Plinth and Haskell. So Plinth is strict, so all the function applications are strict. Bindings, you can have strict and or non-strict bindings. You can use tilde patterns to define non-strict bindings, but there's no lazy evaluation in the runtime. So the non-strict bindings are evaluated by name. And this is the first stage, the front end of the plinth compilation. So we simply just reuse the standard GHC front end. So that shows that indeed plinth just reuses a subset of Haskell syntax. So like I said before, there are two other approaches for doing DSLs. There are standalone DSLs and there are eDSLs. So standalone DSLs are obviously very different, but I do want to talk a little bit more about eDSLs because they are more similar to plinth. So again, eDSLs are just regular Haskell libraries for manipulating expressions or ASTs. And that is the case with both deep embedding and shallow embedding. So eDSLs have a few advantages, like they are highly customizable. I mean, not as highly as if you create a new language, but still, like syntax-wise, there may be some constraints, but semantically is quite highly customizable. Like for example, your host language might be a functional language like Haskell, but your eDSL can be an imperative language, right? That's totally fine. There's no problem with that because you can define your language and AST however you like. And it's also relatively easy to develop. Again, it's just a regular Haskell library, so there's nothing super fancy going on here. And you get meta-programming for free because meta-programming is compile time programming. So your DSL's compile time, your DSL's compile time is just Haskell runtime. So meta-programming for eDSL is just like plain vanilla Haskell. So no TH or anything like that. So it doesn't get any easier than that. But there are some major drawbacks, mainly that it creates some burdens for the users. So users are writing not simple code, but users are writing code manipulating ASTs explicitly. And what that means is, for example, you don't get to use the simple int type. You have to use something like AST of int. And when you need to compare two ints, normally you don't get to use the operator, the regular operator on the top, and you have to use something like the one on the bottom. Sometimes you can recover some of those regular operators, but only with heavy overloading, which has its own complexity. And limited support for pattern matching or branching, because if you write like if then else in Haskell, or if you do a regular pattern matching in Haskell, that branching occurs at Haskell runtime. But Haskell runtime is your DSL's compile time, so that's the problem. If you want your DSL to support branching or pattern matching at runtime, then you have to come up with your own branching operators, which are usually much more awkward to use than just a simple if then else. Having said that, in Haskell, there is a way to recover some of the nice syntaxes because of this rebindable syntax extension. But that also comes with its own problems. There are also other clever things you can do in an eDSL to make it as ergonomic as possible. But I'll just read a quote by Kono Elliott. This is from the paper Compiling the Categories. So additional efforts can hide more of these symptoms, but the cracks still show, and each new coping mechanism leads to increasingly mysterious type errors. So that's eDSL. Plinth, by contrast, is like reuses a subset of Haskell. So the good things about Plinth is that it reuses Haskell syntax without any restriction. If you want to use int, you just use int. If you want to compare two ints, you just use the regular comparison operator. And if you want if then else, you just do if then else. Everything is regular Haskell. And because of that, the code is relatively simple and it's relatively easier to learn and adopt. And transferable skills, because when someone perhaps new to Haskell is learning Plinth, they are also essentially learning some basic Haskell, which is a very useful thing to do. I don't need to sell Haskell to this audience, right? I think we probably all agree that learning some basic Haskell is probably one of the best things anyone can do to themselves. like that it will make you a better person. It will purify your soul, and it will probably add 5 years to your life or more, right? So I think we probably all agree with that. But unfortunately, there are also some drawbacks of this approach. First of all, limited applicability, and this is probably why this approach is relatively more niche, is because now your DSL is much more constrained by what your host language is and does. For example, if your host language is Haskell or some functional language, and you want your DSL to be imperative language, then this approach is probably a very bad idea, because it's not Haskell anymore. And then deep integration with GHC, because now it's no longer a regular Haskell library, right? You need deep integration with GHC, which is tricky, very tricky, because GHC is not designed to compile plinth. So it is somewhat customizable, but not fully customizable, and you really feel like sometimes you're just twisting its arms to make it do things it doesn't want to do. And sometimes I open issues in the GHC repository, and I ask, like, can we make GHC do this or that? And then Simon would reply and be like, why would anyone want to do that? Right? Like so it's tough. But fortunately, we do have. I do have some coworkers who also have merge permission to GHC, so that's very useful. And semantic difference against Haskell. So this is also a problem. So for example, the lack of lazy evaluation means that some of the idiomatic ways of writing Haskell are not good ways of writing plinth. That can lead to very inefficient code. But I don't know, maybe that's a good thing, who knows, because Richard just told us in his keynote that he thinks lazy evaluations are confusing, right? So so plinth has no lazy evaluation whatsoever. That means it's like completely clear, right? So that's plinth. Yeah, that's a subset Haskell. Now, number two, the second thing I said about what makes plinth interesting is that the bulk of the compilation happens in the GHC plugin. So here it is. So it translates GHC core to compiled code. So it goes through a PIR, which is Plutus IR, and then typed Plutus core, TPLC, and then UPLC, untyped Plutus core, which is the final target. The core language here that everything else revolves around is typed Plutus core, so TPLC. So it's a system F omega based calculus with iso recursive types. And there are a number of reasons why we use this as our core language. It aligns well with Cardano's philosophy of predictability and determinism. And it's also grounded in extensive academic research, right? System F has been around for many years. As Phil likes to say, how do you know that your language won't be obsolete in 50 years? Well, use one that was invented 50 years ago, and use one that was invented twice, and that was System F. And then based on TPLC, then came the untyped version, UPLC, which is the final compilation target. And a PIR is a high-level IR, so it extends TPLC with things like bindings, recursive bindings, and recursive data types, which makes it like 10 times more readable and very suitable as a high-level IR. Oops, something happened. All right, here's a concrete example. So on the left, so this is plinth, and here is a function any less than 10. And as you can see, this is just like plain vanilla, simple, basic Haskell. I think anybody can learn to write this very, very easily. And this is PIR, so this is the first step of the transformation. So PIR, as you can see, is fairly readable. It's basically there's this recursive data type called list, and then there's this basically a recursive function Go that operates on the list. And then, yeah, you have a question?
I see a double bar or there. You said there was no laziness.
Yeah, so the only laziness is the Boolean operators like and or. So it's like most other strict languages. So this is TPLC. TPLC is much, significantly less readable. So this is not intended for you to read, because all the nice things are compiled away, right? All the data types, all the recursion, all the bindings are compiled away, and also because of the ISO recursive type, there's a lot of like wrapping, unwrapping. So it's much less readable. And then finally, it gets compiled to UPLC. So this is basically untyped lambda calculus with a bunch of built-in types and functions. So now, an alternative way, as I mentioned earlier, of implementing a compiler for something like Plinth is to implement a standalone compiler using GHC as a library. So what are the trade-offs here? With a standalone compiler, you get a more, it gives you a more first-class feel, right? Because now your language has its own compiler. So you're no longer like reusing GHC to do something it's not designed to do. So more of a first-class feel. Although this point is a bit subjective, and it gives you more control of the pipeline. So now, if you are not happy with the GHC parser, you can just strip it and replace it with your own parser, or you can replace part of the parser. But on the flip side, there's less overlap with standard Haskell development. So for a team or a project that's already invested in the Haskell infrastructure, like more of a first-class feel might be a bad thing, because now you're introducing additional compiler, additional tooling to your stack. And more importantly, a standalone compiler makes it harder to inspect and manipulate compiled code in Haskell. So in other words, it makes it harder to mix regular Haskell and Plinth together in the same project. And this is a very useful thing to do, because oftentimes you want to further manipulate your compiled code at Haskell runtime. Or you may want to test your compiled code using quick check, hedgehog, or whatever Haskell test framework. So this is a very useful thing to do. And to that point, this is a very important use case of manipulating compiled code at Haskell runtime, is lifting. So I'm not going to go into details here, but lifting is, so this is very similar to lifting in template Haskell. So if you know how lifting works in TH, then you know how lifting works here. It basically, you're serializing a Haskell runtime value into your AST. And this is very useful for parameterized contracts, because there's a parameter, runtime parameter, that you want to put in your contract. And the key point is that the plug-in approach conveniently allows this, where if you have a standalone compiler, it makes it much more difficult. Okay, so let's move on to the runtime, the UPLC evaluator. So it's a performance-optimized implementation of a CEK machine. And this evaluator lives in the Cardano node. A Cardano node is basically a computer or machine running the Cardano blockchain protocol, right? So inside the node, we have this CEK machine that processes UPLC or Plutus scripts. So UPLC and Plutus are, they mean the same thing. So you submit your Plutus scripts to the node in a transaction, right? So you put it in a transaction, you put, where you specify a Plutus script and your expected cost, and you submit it, and the node validates the transaction. Part of validating the transaction is to run the script. And when running the script, there are a number of possible different outcomes. The happy path is that it succeeds with the actual cost, or it may fail because perhaps the budget is exceeded, or perhaps some validation condition failed, or perhaps the machine got stuck, which means no transition rule applies, which means your UPLC program is not well typed, which cannot happen if you compile it from Plinth, but it certainly can happen if you compile it from a different surface language, because there are a bunch of other languages, or it can also happen if you write the UPLC by hand, right? So these are the different outcomes. And then predictability. So here I picture the CEK machine as a slot machine, which it's of course a joke. It's in reality, the CEK machine is like the polar opposite of a slot machine. So everything is like completely not just deterministic, but also predictable, in the sense that you can, before you submit your transaction, you can test it offline. You can test it off-chain. You can run the CK machine off-chain, run your script, and if it succeeds off-chain, then it's guaranteed to succeed on-chain. So which is a very nice property. But I mean, you might wonder how that is possible, right? Because surely the outcome of executing a script must depend on some kind of blockchain state, right? For example, the current time, or whether you have enough money in your wallet and things like that. So how can you completely predict this? And the very short answer to this is that the outcome of submitting a transaction is not predictable, right? So the transaction may fail because timing constraints are violated, or maybe because there's not enough money in your wallet. But in those cases, the transaction will be rejected immediately without running the script. So the guarantee is that if your script is run, then you will know that it's guaranteed to succeed, which is very nice property because running the script is the most expensive part of validating a transaction. So you don't want to waste any money by running your script on-chain, which you have to pay for, only for it to fail unexpectedly. So this is completely predictable. So here I just want to flash you some code fragments of the UPLC evaluator, and the point I'm trying to make is that it is quite readable and high level. So there are basically two main functions: compute CK and return CK. So this is compute CK. And as you can see, even though we need to squeeze the maximum performance out of this, the code remains pretty high level, pretty readable. And this is return CK. In fact, I mean the code is so readable that when other people want to implement their own own UPLC evaluator CK machine in a different language, they tell us that they often use our Haskell implementation. They often refer to the Haskell implementation as their reference, even though we have a formal spec of the CK machine, and we also have an ACTA formalization of the CK machine, but they still prefer to read Haskell. So that goes to show you that Haskell is indeed very well suited for implementing something that demands high performance, like a blockchain VM, without compromising readability. I mean, either that or that our spec is very badly written, but I think it's the former. Now a little bit more on squeezing out performance. So these are some of the things we do for squeezing performance, like band patterns, tilde patterns, inline, no inline, unpack, and things like that. So these are of course not trivial because in different places you want opposite things. Sometimes you want band, sometimes you want tilde, sometimes you want inline, sometimes you want no inline. So it's not trivial, but the good thing is that these things they are mostly just like pragmas or things like that. They don't really compromise readability. So your performance optimized code remains fairly readable, and I think this is a great strength of Haskell. But the process is far from trivial. It involves lots and lots of reading GHC core, because that's the only way to reliably know whether GHC does the things you want it to do. I think Richard also touched on this point in his keynotes, is that optimizations in GHC is more like black magic, right? So sometimes you add an inline pragma, but for some reason GHC refuses to inline it. And sometimes an optimization may fire for one piece of code, but it may not fire for another very similar piece of code. Or sometimes things may change if you put a function in a different module, or if you export different things from a module. So it's very subtle. The only way to know for sure is to read GHC core, which is something we spend a lot of time doing. But fortunately, I mean, GHC core is fairly readable. Like I think among all the IRs used by all the compilers, I think GHC core is like fairly easy on the eyes. I mean, it's not even that different from the surface language. So lots of reading GHC core. So this future work, I think arguably the most important thing right now is the first one, which is more front-end customization, because like I said earlier, we are right now just using the standard GHC front-end with no customization, and that creates a number of problems. And I think more front-end customization will, let us do things like catching unsupported Haskell features earlier and generating better error messages and things like that. And then other architecture options we'd like to explore, including the standalone compiler option that I mentioned earlier, and or maybe going the other direction, which is even tighter integration with GHC. How about maybe making the Plinth compiler a dedicated GHC backend, like the JS backend or Wasm backend. So that's an idea. And language features like laziness and modules, these are also very useful. So for modules, actually, there's a very lengthy and very detailed, very nicely written proposal about this, written by John Hughes, and it's actually quite fun to read. For laziness, we don't have much idea right now, but I don't know if John wants to write another proposal or not, but I guess we'll see. So let's get back to what makes Plinth interesting. So I talked about the first three. Let me just briefly mention the other three. So compiler optimizations would be, it's interesting to look into Plinth's compiler optimizations, especially in contrast with GHCs, because even though Plinth reuses a subset of Haskell, the different use cases and different runtime requires very different optimization choices, and this could offer some useful insights if you're developing a somewhat similar language. And compiling data types, so there are three ways that to encode data types in UPLC and with different trade-offs. And these are also implemented in very different ways. So there are some interesting stuff there. And the need to predict execution cost accurately is perhaps a unique challenge for a blockchain language. And that certainly put a limit on what we can do and what kind of language features we can offer. So more details about these are available on in the paper or in the repository. So let me just end by saying that what Plinth shows is, I hope, not just how a particular language can be implemented in a particular way, but also a demonstration that Haskell is very well suited, if not particularly well suited for powering a global scale system like a blockchain, which millions of people use and rely on. And so, as the Haskell community, I hope we can, continue building upon these ideas and take them further and, continue to demonstrate the value of Haskell in the years to come. And these are links to some of the things I mentioned earlier. And thank you very much for your time.
Thank you for your talk. So when you compare the different approaches of doing DSLs, I think apart from all of the other considerations, one of the key factors that you actually had a successful story is that you had a team which is highly, has great expertise in GHC development and is tightly integrated into that GHC developers community. So is that a takeaway for me is that don't ever try this approach if you don't have that team?
Yeah, exactly. So Plinth is particularly attractive to teams that are already invested in Haskell infrastructure and Haskell knowledge. And unfortunately, that's probably why Plinth is not the most popular Cardano smart contract language right now, because such teams are rare. So Haskell is relatively niche, which doesn't really help.
Let's thank the speaker again. So for the next session, the authors for the first talk unfortunately have to cancel their talks, so we will start at 4:20 here again, and there will be followed by a chair's report. See you later. Welcome to the last session of the Haskell Symposium. So we'll start with the first talk by Song Zhang, who is going to tell us about something about type classes. Take it away.
Hello. Hello, everyone. Today I'm going to talk about derived class instance top-down and derived TTG. Okay. Oops. What happened? In programming language like Java, you use a package called Lombok so that the user can write some annotations to generate two-string functions and equal and hash code functions automatically. And in Rust compiler, they introduce this derived attribute to implement traits automatically. Traits are some concept like Haskell class. So you write derive partial equal or clone trait, then it will generate the code for you. And in Haskell, we have multiple deriving mechanisms in GHC. Like we have built-in deriving mechanisms for common classes like show and equal and order. And we have generalized new type deriving to derive a, sorry, this should be new type. So for data type with one constructor and one field, we use this new type deriving stuff. And also we have generic programming techniques and derive any class. So if you want to serialize this data type T, then you can derive generic type class and then binary instance here. Then you will get encode and decode function that can be applied to TA, right? Also, template template Haskell-based approaches like ASIN library. You use some meta-programming function, derive JSON, and to make from JSON to JSON functions generated from this code. Also, we have deriving via an instance via a model template by using this language extension. Also, we have many more language extensions in order to derive class instance automatically. So there are basically about 12 out of 130 language extensions related to instance deriving in GHC 9.10. So it's about 10%. I know the slogan is being lazy with class, but recently I understand in this way by not writing class instance code as possible. When I was writing Haskell code, I encountered a problem. Current deriving mechanism focuses on only one instance and one class deriving. Then if you have composite data types, like 100, let's say, like it's an AST, the data types are composited together as a whole. And each of which needs a deriving clause. Sometimes it can be a pain to write those deriving stuff, right? And also we have one class may have multiple superclasses. Like I'll give you an example later. So when I handle this problem, I just write a standalone deriving from the top level type and see the errors emitted by GHC and do some interactive programming. This is not a good experience. Possible cases may be in Haskell AST in this package. There are about 78 data types. Imagine you need binary instances to serialize the AST into your disk or send over the internet and want to encode the AST with JSON by using some template Haskell techniques in ASIN package. then you need to write a lot of trivial code. For superclasses, imagine you have this data type, like wrap with this double with a constructor, and you want to make an instance of real float. And there will be many superclasses, and I can't remember them all, and I still need to interact with the GHCI. My early solution is like this. I use macro to write down the data types. However, there's a problem with that. If the data types are from a third-party library, then you can't, force the third-party library to write the code like this, right? And you can't change the third-party library, actually. So pretty bad, actually. The idea is that we can just traverse the data type declarations and generate the instance declarations with template Haskell. We provide 4 kinds of APIs. First is to generate empty instances declaration for the default instance provided by some generic programming techniques. Even though we have derived any class today, I still provide this API. And we can generate standalone deriving declarations of types by using built-in mechanism of GHC. Also, you can use some template Haskell techniques to traverse the data declarations and apply the template Haskell function to generate all the class instance. And generate a class and a superclass instances for one type. So I provide these 4 kinds of API. I'll let's see the 4 kinds of API. For instances, just you provide a class name and a type name. I will give you the declarations. And here, the functions with this with, end with word, you can give some parameters to specify, to do some customization. I will talk about this list and this context generator in later slides. Because as you can see here, we need context generators, but in template Haskell, we don't. And for deriving superclasses, you just need to give class name and type name. It will generate the instances for you. So my sketched algorithm is that for a given type T, we need to generate an instance of class C. First, we check if T is an instance of C, or the instance of T is generated by our algorithm. Then we do nothing. Otherwise, we infer the T's class instance context and generate the instance declaration. And for each type constructor in this type T, we kind of traverse the types, and we apply this process recursively to generate the data declarations. The bold part here and here highlight 2 issues we need to solve. One is the instance function in template Haskell library. It doesn't work with polymorphic types. We have to solve this. Second, we need ways to infer the context in the standalone deriving declarations. So for the first problem, instance is not working on polymorphic types. So if you put this kind of code, say for all equal A and a list of A, you ask whether this is an instance of equal, the function will return false. It is not in current GHC implementation. But Ryan Scott suggested that we can use any instead of this polymorphic parameter to pass it into this as instance function. It will return true. So
this is kind of a trick to solve this problem. Then I use SYB library to substitute all the polymorphic type variables with any type before applying its instance function. Then this problem is solved. Problem 2, we have to infer the context. But normally we do not need to write the instance context here or here, right? However, for standalone instance deriving, you have to write some context here, right? We have to, field or inferred, since we have to use standalone deriving. But for APIs with template Haskell, the callback function will infer the instance context. So that's the reason why we do not have the context generator parameter with this template Haskell API. So how can we solve this problem? Ryan and R.W. Barton noticed that we can just leave the type, leave the context as a whole there with build card here. But we need to enable a lot of language extensions, and the GHC will infer the context here. So in this case, GHC will emit warnings. And my question is that okay to just remove those warnings by default? Because normally I do not care about the type which is filled by the compiler here. The second solution is we just put all the field types into the context. Like if we derive show instance for list of A, this new data type, we put all the fields, this field and this field, into the context and give to put a show list here, right? So we put all the fields into the context. Then for the HS module, it will be this, and module name and special con or q, then put a q name here. These are all the fields of q name. So we put all the fields into that, then we can solve the problem, right? However, I want to infer the context a bit, so I introduced a structure. It seems to be very complex, but I will give you a concrete example later. So in my data structure, I use I. It is a set to store inferring types. I use P. It is a map from type names to the type parameters. This can be initialized before the generation process. And F is actually some context field types. During the inference process, I will substitute these fields interactively with traversing the data types I need to infer. I will give you an example later. S is a substitution type which keeps tracking of the substitution field in a data type. And R is actually the result store inferred data context to avoid duplicated inference. I will give you a concrete example. My concrete example is here. There is a P and there is E and there is a proxy-like type. And this P has only one field here. So I is inferring the type we are inferring. So P is the type we are inferring here. And the P is the parameter of the type. We can initialize by this one, right? By P, there are two type parameters. And for E, we have X, Y as type parameters. For PX, we have Z as the type parameters. And we put the fields into this F. The goal is to eliminate kind of this E and to see, look into this type and this type. And we construct a substitution, and this substitution is constructed from P because in this E for this type A is from X, for this PXB is from this Y. So we construct this kind of substitution here. And next, we can't do anything because we haven't inferred E. We put E into this I. And we put all the fields of E, which is this X and this Y, into this F. And the E only has only type variables. So the inference terminates here for E. So we will put it into the result here. And now what do? We can substitute, we already know the fields, context field of E. Then we can somehow substitute this fields of E with this substitution. And in this way, we eliminate E in this F for P. So we have A and PXB here. And next, what do? We infer PX, the context fields of PX. And the PX, we do not need anything because there's the type parameter is phantom. We do not need anything here. And when we do the substitution for this PXB, then it vanishes. So we eliminate this PX. For the fields of P, we need only A. So we eliminate the phantom type parameters. We only keep only the necessary data type in the result. So, however, the implementation has bugs, and it cannot handle mutual recursive types very well. I still need some work. And currently, it doesn't work with Haskell source ext. But it seems to work fine with ST types in Haskell SRC and the GHC ST types. So next, we need to talk about the generation control. Normally, types like integers, like some other types, we don't deriving a class for them normally, right? Imagine you have a class called a number of data constructor, and that can return the number of data constructors of an algebraic data type. This class needs no instance context, and the generation process might need to stop on integer, right? Here is my class, right? And for this integer, we have to stop the generation. Then you can put it into this list. Then the generation will stop on the integer type. You need to some sort of control of the generation. And another example is non-exported data constructors. You can't look into a constructor that is not exported, like a ratio. When you have this type, right? You want to derive like generic. Then this data type, the constructor of this one is not exported. So the generation has to stop on ratio. You have to control it. And superclasses, it's very easy. You just write deriving superclasses and real fract, and you will get all the superclasses here, right? But for mutual recursive types, you have to write them together because there is a staging problem. Okay. And here I suggested to use derivings to write to specify the two types together. Okay. So the future works of derive top-down. Maybe I'll give an API function to derive all the dimensions, the superclasses and the types, and infer the context correctly, and add a language extension maybe called type family context. I'm not sure this is a good idea to put a type family put type family into the instance context by the compiler. Maybe I should implement this as a plugin. And maybe during the implementation, I find I have to import a lot of data types. Maybe import top-down is a good idea. I'm not sure. And next I want to talk about TDG generation. The TDG generation is...
I think you may want to wrap up soon.
Okay, yeah, 2 minutes.
1 minute.
Okay, the TDG is, you can just derive TDG automatically, and you just specify the types. It will generate the type families and the extensions for you. And you can do some simple decorator and specify the type equations, what is on the left type and what is the right type and the default type. It will give you this type family declarations. And if you want to more control with the decorator, like here, you have to pass into a callback with the argument as this type variable of the type families. So it's in this way you can generate some the TDG automatically. And in the future, I may consider to generate pattern synonyms for the TDGs. And this is the project URL. And I want to thanks to Ryan Scott and Richard Eisenberg for discussing the issues with me. Okay, finished.
Questions? Yes.
Hi, nice work. You mentioned there were some compiler warnings that came out when you used an underscore, not gave something a name. And that reminds me that this shows up in code generation, in metaprogramming quite a lot, where something deserves to be a warning if it's written by the user, but it doesn't really deserve to be a warning if it's written by a code generator. Do you agree with that? Do you think that's the case here, that these are probably not worth a warning because they were automatically generated?
I think even this is not generated by the compiler. It is written by the users. We shouldn't give any warnings because I just don't care what the type is normally.
Oh, I see. So for everyone, even for human users, this shouldn't have a warning. Thank you.
Maybe let's take one final question when the next speaker
But I mean,
says
if that's so, you can just turn off the warning. Like if you, I thought that the whole issue here is that you don't want to turn off the warning because if the human writes a type that uses partial type signatures, you still want to have the warning.
Yeah.
So yeah. So I think you're right. Yeah.
Yeah.
All right. Let's thank the speaker again. All right, our next talk is going to be a very exciting talk on machine learning. Take it away.
of course. Check. We're good? So this is what you can think of this doing is Haskell as a basic model type where you can run it and do a backpropagation gradient. You can chain models very naive. So this is a naive implementation. You can chain them by chaining the running function and chaining the backpropagation. This is, by the way, the entire like backprop algorithm. So this is what you might think of doing this. So and also if you use a AD library, you can even make it easier. A model is just basically a basic function. So all it looks so far so good at the simple, naive level. Your loss function basically values the loss and then gets doubled to optimize against. So once you get that, you differentiate the optimizing the double and you backpropagate. So far so good. You can chain this pretty well. It's very composable, very beautiful. My first attempts were like this. So it's a solved problem, right? Haskell is conquered machine learning. Actually not. So let's add parameterized initialization. You have to, each parameter has to be initialized somehow. So when you make your model, you have to say how you should start your model with the basic parameters. More features, we want to regularize, so that can look like a P to double function that gets you a differentiable running total of things to optimize against. And kind of showing you that this is getting it's doable, but it's getting more and more layered and more complicated. And also modern models, they add noise and weights. Maybe when we want to like add a nudge to run during training to nudge the parameter a bit. We want to add random noise or do random scaling. But this function does not compose, so we can no longer write chain anymore. We can't compose these anymore. We have to like, maybe we can chain them in a gadget with like essential variables, and that could work. But the more we try to fit this into this box, the more ugly and bad it gets, unfortunately. So this doesn't work. And the problem is that most libraries and even Python these days have the same issues. So models have to declare all the capabilities up front, all the noise, all the regularization, all the parameterization, all the backprop functions up front. Every model has to know about all the capabilities, and the composition is inherently existential. So models have to be essentially composed with their internal functions hidden inside a chain of hidden variables with dynamic dispatch. There must be another way. There has to be another way, right? And that's why I'm here. So what do we actually need? Like, what are we looking for? We want to selectively integrate actions of multiple capabilities, parameterization, backprop, regularization, all that stuff. We want to run these in different contexts, right? When we're training, we want to have regularization and noise. When we're evaluating, we don't. When we're initializing, we only care about new parameters. So we have a lot of actions. We want to defer them to runtime. And we want to compose actions of variant capabilities, right? We want model A and model B to compose, and their capabilities will merge together in the sort of union of capabilities, right? So if one model has regularization, the other doesn't, we want them to compose to have a big model that does do regularization. And does this look familiar with another like space of Haskell research? It's in the title. This is actually basically extensible effects, right? So everything we talked about seems to be perfectly fitted for extensible effects. And as far as I know, there's no other research combining extensible effects with machine learning capabilities like this, which I think is interesting. So come with me on more of a exercise of the imagination. The type signatures coming up are not exactly going to be, I don't expect you to understand all the code, but imagine what if we did this? What if we put everything together? What do we gain from this, and what do we learn, and where does this open? So we do know that thanks to Jesse Siegel's great doctoral thesis, that AD itself is an effect. So if you use the effect library, you can have variables that you can differentiate. So assigning variables that you can differentiate and tracking them throughout the life of a program, of an F program, is very doable and very efficient. And Jesse goes through multiple ways of doing this in an effective way. So backprop itself is already an effect. So the main machine learning thing, backprop, already solved. what else can we do? We can add parameterization as an effect, right? Maybe an effect could be initializing a parameter, initializing a new matrix or a new vector, can be initialized under namespace as an effect. So as an example of how you could write this as a library, let's say your model is just a function from A to B, a Kleisli arrow in the effect monad. Then you have a model already that does like a feed-forward neural network. You compose them very simply by just having layer 1, layer 2, layer 3, feeding the values through each other. So this is like a nice way to compose them, and there's no longer any mixture of, it's a monadic Kleisli arrow, is very clean, and you look at it and see it's very clear where the data is flowing. So this is nice, but yeah, so we can run these as eliminators, and the idea is that when we train a model, we eliminate the F. When we run a model, we limit the F with different handlers. So in training, we eliminate them with our training, our noisy handlers, and we run them with our no-op handlers, for instance. So no noise, no anything when we're running a model. And that's done by just handling the different dispatches. So let's look at what we can gain out of this. So what actually happens when we do this? Well, how does our mind open if we do this? So all models end up being just Kleisli arrows. So all machine learning models, from the biggest LLMs to the smallest iris dataset classifiers, feed-forward neural networks, are just Kleisli arrows in F. And models declare their effects. And when you combine models, the type checker combines effects by just combining type class constraints. And if we put B-vars, the differentiable values, so think of B-var as a differentiable value in effects, what does this give us? So what if we had B-var, a state of B-var, or a reader of B-var? So I'm gonna kind of give you my Hamilton Bridge moment. This is my story. I was walking down the park and I was thinking, wait a minute. What is writer sum B-var double? Does anyone have an idea of what this might be? So imagine that your effect is just a writer of a summed differentiable value. This actually is regularization, right? So you have a running total of differentiable values, and every model can write to the writer, because the B-var is tracked as a derivative. So if every model just writes and tells to this running total, that writer, that log, is also differentiable as well. So by just using normal Haskell things, these Haskell monad transformers and effects correspond to machine learning properties that we hadn't explored before. So we have a regular effect, we can have like a tell of organization. We can choose to regularize an L2 or an L1, and in training mode, this is a writer tell, and in inference mode, it's just a no-op, right? We don't care about regulation in inference. So you see that these normal Haskell concepts that we've been using all along correspond to these ML effect concepts as well. So yeah, so if we tell from the parameters, we get organization. If we tell from an actual output of a model, we get layer normalization. So we start matching all of these exotic terms that they invented in these ML papers are just basic writer or basic monad transformer concepts in Haskell. And it's basically a zoo of different things that you can find in these papers. Stochastic perturbation, noise injection is just adding a value, but we can get injection of multiplicative noise, which is what dropout is, and other terms like that, are a transformation on differentiable values. So I'm basically condensing all these terms are, if you read the ML model, there's a billion terms that they give out names, things like dropout. All those are condensed to basically very simple Haskell concepts, as long as we have differentiable effects in our stack. And we can have a batch effect, which is not another major concept in ML. We can have reader-like context, which means we can thread things like annealing parameters, training rate schedules, different type of parameters. So I'm giving these as like very ridiculous words, but all these are real words that they use in ML. And they correspond to this basic Haskell reader, writer, state type of values. We can even thread arbitrary signals from runners for observability. So the basic idea is that all of these zoo of effects, if we imagine them in a better world, they're just normal extensible effects. And they combine very well in Haskell. I have a library implementing this that I hope to release soon. But because we can now throw in derivatives in our effects, all these effects correspond to interesting ML concepts. And I leave your own journey, hopefully it opens your mind to exploring these concepts under this new framework, this new idea that we can do. These code snippets, I've implemented them in CPU. It's mostly conceptual. There's no attention to benchmarks just yet, but hope I can find meaningful benchmarks to do with just CPU and GPU programming. And future work, I hope to polish and finish up the library, mostly just to have a nice declarative semantics. And I want to basically classify all these ML primitives across the thousands of papers as just basically normal Haskell reader, writer effect patterns. And I believe it is possible. We must believe. And maybe even GPU programming as sensible effect as well. Yeah, that's for questions. I write a lot on my blog about this stuff, so if you follow blog.jly.im, you can follow along with my ventures.
Questions?
Is this not published somewhere? Because your Hamilton on a bridge moment seems to be valuable enough to be written up.
It is in progress. I have a paper, but it's not published yet, but it's in work, yes.
That we're using effects to build up these models, is there enough structure there that we could also interpret these into some kind of representation that then gets pushed into some other efficient library for doing these things? Or?
Yeah, the main problem is that effect monad, the bind function is like a Haskell function. You can only go so far. By picking the right new type writers, you can make certain things no-ops in Haskell, but as long as you're in a monad, you're kind of stuck with the Haskell function as like the determining thing.
There's been some other talks during ICFP on similar issues and not using monad as the sort of underlying interface for these things, like using arrows or categories, which should give you a little bit more access to that that structure, I think.
Yeah.
I don't know. I'm just an everyday Haskell programmer. I don't know.
I think actually, like, the set of functions you actually need to write are very small, so it's very doable, I think, to actually like defunctionalize to a level that can be compiled effectively.
All right, let's thank the speaker again.
Thank you.
Let's thank the speaker again. So next talk is a remote talk that was moved from yesterday to today. We have everything set up. Can you hear us?
Hello? Yes, I can hear you very well.
Okay, cool. Maybe let's get started. So we have a talk on typed Karen. Yes, please take it away.
Okay, thank you very much. Thank you for the opportunity to present our work, joint work with Artem Starikov on typed Karen. So typed Karen, statically typed relational programming with exhaustive matching in Haskell. So a little bit background about mini-Karen. So mini-Karen is a family of embedded relational programming languages. It was first introduced, I believe, in scheme programming language by William Byrd in his PhD thesis. One interesting feature of mini-Karen as a representative of logic programming languages is that it features fair disjunction. That is, the search space is traversed more or less similarly to BFS rather than DFS as it is done in, say, Prolog. Now, Minikanren is embedded, and it has implementations in many programming languages, including Clojure, Kotlin, OCaml, Rust, whatever language you prefer. And since it is embedded, one of the cool things about it is relatively easy to bring it for logic programming in actual project, rather than bringing in heavy standalone logic programming languages. And moreover, there's a version of Minikanren called microkanren, which is a smaller core that can be implemented in most programming languages in one sitting. So you don't even have to reuse an existing implementation. You can do it yourself. And so a quick example of Minikanren is a relational version of appending to lists. So it's list concatenation. Now, since this is a logical programming language and not just a functional programming language, you have relations. So your outputs are also arguments to your relation. So here we have a definition of appendo, a relation between three lists. And this relation basically says that the last list, ZS, is a concatenation of two lists. And you can see the two branches here, what happens if one of the lists is empty and what happens otherwise. Now, the important part, of course, as in any logic programming language, is that you have these modes for arguments, and you can run any relation with unknowns in different parts of the relation. So, for example, you can run this concatenation in sort of forward mode in the sense that you have your two input lists and you want to ask what is the result of concatenating them. Or you can give the result of concatenation and then ask, for example, which two lists can provide you with the concatenation that is 1, 2, 3. And then, of course, you will have multiple solutions. And so in general, running these relations will give you a stream of possible answers. Now, typed Kanren is a dialect of Minikanren embedded into Haskell specifically. And the main features, I guess, are as follows. So typed Kanren supports all of the core functionality of Minikanren, and it supports disequality constraints, which is important for dealing with negative relations, like something is not a member of something, for example. It is statically typed, and it's not just statically typed because Haskell is statically typed. We also have types for relations, and we differentiate between the types of logical variables. And we support user-defined types. And typed Kanren offers some support via GHC generics and template Haskell to reduce boilerplate when you want to use your own types. And we offer a thing that we think is relatively novel, which is exhaustive relational matching, which I'll talk about later in the talk. Now, there are already existing Minikanren implementations in Haskell, but most of them are untyped in the sense that they have a type of terms, which is predefined, and then you can only do logical programming within this predefined type of terms. Now, there is another project called Molog, which appears to be unfinished and abandoned, which tried to do the very similar thing to what we have done. So you can compare with that. So here's an example of the same relation appendo written in basic typed Kanren. So here we have disjunction of two possibilities, and you can see that every possibility is written with the do notation, where we just specify sequentially the constraints that we have on our input logic variables. For example, in the first branch, we say that X is an empty list, and then if X is an empty list, then of course the YS and ZS should be the same. And then in the second branch, we introduce fresh logic variables and then say, well, if the first list is a cons of X and XS prime, and then ZS should also be a cons of X and ZS prime, such that XS prime concatenated with YS gives us ZS prime. Now, the feature that we, sort of one of the distinctive features of type kernel that we introduce is combinators for relational matching that are similar to match-E in the original Lisp implementations of minikanren. But beside the typed version of match-E that already has been described before, we provide an additional version that also supports exhaustiveness checking, making sure that we have covered all the constructors that are present in the user-defined type. Now, to the best of our knowledge, none of the existing types implementations of minikanren have even support of the match-E, never mind the exhaustive version. So here's an example again of the same appendo, but now defined with matching. So here we're using exhaustive relational matching with this match-E prime combinator, and access is given to this match-E, so we're matching on access, and then there are two patterns, both of which are prefixed with this on prime combinator. So we're checking if the input list is, if XS is empty, then YS should be equal to ZS. And if XS is a cons, and these are the components of that cons, then we introduce a fresh variable ZS prime, make sure that it's a cons, and make sure that XS prime plus YS, it gives us ZS prime. The final thing, enter, just wrapped around. So as you can see, this is not a built-in case that we are able to use here. We have to use our own sort of set of combinators. Match-E sort of completes matching on one side, and enter starts this pattern matching on the other side. And so everything in between are the branches that we are pattern matching on. So to briefly talk about the core of type kernren, from the user perspective, type kernren consists of the logical type class. This is a type class that specifies a logical counterpart for any given type, as well as necessary methods for the type kernren to be able to do the unification and search. There's a Go monad, which is a context in which relations are combined, as you have seen the do notation used in the previous slides. And there are, of course, utilities to reduce boilerplate for the logical type class. So to understand why we need this logical types versus regular types, this is a problem that occurs specifically in a typed, statically typed setting. So for example, if we have a tree data type on the left, if we want to use that trees in a logical program, now we need to specify which subterms of this tree are allowed to be unification variables or logic variables that are going to be learned about in the process of unification inside of the logical engine. Now, for that to work, we need to replace these subterms, and by default, for example, we can replace every subterm with the type term parameterized by the original type. And what this does is it says that we either have a value of type A there, or we have a unification variable. For recursive use of tree A, it's a bit more subtle than that, because we don't just want to have a tree A or unification variable, we want to have a tree A where, again, in any of the sub expressions, we can also have unification variables. So how term is essentially described as a sum type, where it is either a unification variable or it's a logical counterpart of the original type A. And so the logical counterpart comes from an associated type family from a logical type class. And we demand that from this logical type family, we can uniquely determine which time this originated from. This is not a data family for technical reasons, but this is one of the design choices that we've made. And there are a bunch of methods here that define how to properly do the unification, how to check the occurrence of recursive occurrence of the unification variables inside, etc., etc. Now, importantly, most of this can be done automatically via GHC generics. So the instance can be derived via GHC generics, and the type can be constructed using template Haskell. So here's an example of an instance of logical instance for a tree. So we do here. What we do here is we define the logic counterpart of tree is going to be L3A that we have seen before, and then there is a standard definition for all of the methods. So the Go monad, where we combine the computation, follows the standard implementation in all of the minicanon, all of the other minicanon implementations, with a minor difference that we actually turn the Go monad, from a function from a state to a stream of states to an actual monad by adding the result in the end in the stream as well. Now, this is helpful for several reasons. One is generating fresh unification variables is a part of, works inside of a Go, and the new variable is returned. That's going to be the result. But also this enables the use of the do notation, which makes writing some of the type concurrent programs very concise. So streams here are specifically the so-called immature streams that are either done or yield something, or they await the result. So the await here is important for the fair search strategy in type concurrent, so that we can do sort of a BFS on all of the branching that happens inside of the relations. And the state, just to make it clear, consists of the known substitutions for variables at the moment. It also contains the disequalities, which are constraints on what certain unification variables should not be equal to. And this is important because, unlike Prolog, with minicanon, we cannot do negation as failure, and instead negation is done through these disequality constraints. And there is a maxvar ID just to keep track of the last available identifier for fresh variables. So here's again an example of a relational program in, this is an example of a functional program on trees that counts the number of, collects all of the leaves in a tree. And as you can see, this is written very easily with the case here. Now, we can write this with a disjunction and then specify each possibility in a separate branch. And instead of pattern matching, we're going to have these unification constraints, which are written immediately as statements in a do notation. And this is the code that is equivalent to what we have seen on the left. Now, we can run, again, this program forwards, like we've seen before, or we can run, and we can convert the logical results. We can also extract, or try to extract them, into the actual Haskell value, so that we can convert, so inject here converts the Haskell value into the logical counterpart, and extract converts it back from logical counterpart to Haskell variant. And of course, we can run the same backwards, where we say, well, if the leaves are 1 and 2, which trees can have these as this set of leaves? So it works in either direction. Now, I want to talk very briefly, I guess, about relational matching. The main idea is that we would love to use the case expression that is built into Haskell, but unfortunately, the matching in a relational way should not only be able to work in one direction. It should also be able to generate all of the cases if the input variable is unknown. And for that, we could not have figured out how to reuse case in some clever way. So instead, we have borrowed an idea from a total library by Gabriela Gonzalez, where prisms are used instead to have a sort of total version of case, but with arbitrary constructors like prisms. Right. So I'm gonna show just a very simple example here. We have a result AB, and we have prisms OK and fail for that to pattern match as a sort of first class patterns for the result data type. And then to enable relational matching, we specify match E that takes a term and tries to pattern match on it. And by default, match E doesn't have any alternatives. And then we can add on these alternatives or patterns with a specific combinator called on, which takes as one of its arguments a matching for all of the other alternatives, and it just adds one more alternative with a given prism and a given handler for what to do if that prism actually works. And so in the end, we get an extended matching with one more alternative. So for example, again, the example with leaves will work something like this, where we specify each alternative using on. Now, this version of match E works, but it does not. But it is not total. It doesn't check that we have actually verified all of the constructors. And for relational programming in general, this is fine. But sometimes you still want to make sure that for a particular version, you have traversed all of the possibilities. So for that, we introduce exhaustive prisms, which are variants that are tagged by some information that's tracked on the type level for tracking exhaustiveness. And again, this trick is essentially a variation of what happens in the total library. And so we define our own versions of these prisms, which then specify so logic leaf in particular is a prism that works with L3. And then we have a version of on that specifies the same thing, but it now converts some of the type information, and specifically it converts the cases from remaining to checked once we introduce a certain prism. And we have versions of match E and enter. And match E now has this type class constraint exhausted, which verifies that all of the patterns have been matched. So, and again, here's just a quick example of how that would work. I'm going to skip this type information just to avoid getting overtime. And I just want to talk one last thing about performance evaluation of the type canron. Now we have compared our performance of our implementation against faster minicanron, which is the standard implementation in Racket. This is the default one that is used. There's also OCanron, a typed version of minicanron embedded in OCaml. And there's also KLogic, also a typed version, but embedded in Kotlin. So we have compared this using relational programming for arithmetic and Quine generation, so generation of programmers in programs in Scheme. And the results are as follows. The fastest implementation remains to be the faster minicanron, the Racket one. The other ones are significantly behind. And our implementation fares more or less against KLogic, and it's slightly slower than OCanron, at least on these examples. But you can see that, for example, for Thrines, our implementation degrades much faster than we would love it to. Now, for the performance, we have tried several approaches to improve it, and in particular, there's an interesting approach that OCanron takes to improve performance that unfortunately, due to the laziness in Haskell, is not really transferable to us. So I'm not going to get into the details of that, but just going to mention that there is something interesting to be done about performance that we have not yet been able to do. And if you're interested in helping us figure that out, you're welcome. So in conclusion, we have an embedding of minicanron in Haskell, a statically typed non-strict, statically typed version of minicanron. We support user-defined types. We provide a type version of match E using prisms, and of course, an exhaustive version of that. We assist the user with generating logic types with metaprogramming tools built on top of template Haskell and GHC generics. There are a few things that we would love TypeCanron to obtain, but perhaps the most important one that I'm going to focus on today is the performance. We are sort of a little bit out of ideas of what prevents Haskell from being on par with OCaml or Racket. If you're interested in this project and would like to help us figure that out, just contact us. So that's going to be it. Thank you very much, and I'm open to questions if there's any time for that. And at the moment, I cannot hear any of you.
Hey, can you hear me?
Yes, I can hear you now. Thank you.
You were lamenting earlier that you can't use an actual Haskell case statement for the pattern matching. Since you're already using template Haskell for other stuff in the library, could you have some kind of template Haskell construct where you write a case and then
yes.
It transports that into the code you showed with the match operators?
Yeah, absolutely. So there are two things to say about this. First is quasi-quotation is possible, and we can of course offer any syntax, including case inside of quasi-quotation, to make that work. But we're hesitant to do that because we wanted at least the first version of TypeCanron to not enforce the use of template Haskell on the user. So this is why we went in the direction of exploring prisms instead. But yes, definitely template Haskell can be used there. Another way that template Haskell can be used here is to go one step further and automatically convert existing functional programs with case in particular into their relational counterparts. So if you have already an implementation of append, you could automatically turn that using template Haskell into a relational version. So that, of course, also would help tremendously. But again, this is already pre-processing of code rather than exposing the user to purely Haskell primitives.
Right, yeah, that makes sense.
But that's definitely a future work.
Let's take one more question.
Does it support concurrent evaluation of relational programs? Like sharing the same variables?
So there should not be a problem here because so we have these states which are purely functional. It can be shared easily. We did not try to run the proof search in parallel, if that's what your question is.
Well, I mean, the user could decide what parts of the program they want to run in parallel.
Right. So the user here runs these relations through a specific combinator called run, and within this run, all of the unification variables are local to that specific execution. So you can have multiple concurrent threads in Haskell, and everything will work, and you can run this separate. So unification variables are not global, if that's
no, I mean, what I want is
asking.
to have two threads that are sharing the same unification variables. So one thread could, say, bind part of a
structure and another thread could find a different part of that structure.
Right. Okay, I see. No, that I think is would not work out of the box. No, I don't think so.
Okay, thanks.
Maybe we can take more discussions offline. All right, let's thank the speaker again.
Thank you very much.
So that was our last technical talk, and all right, so the final thing we have is a PC chair report. And first, I have many thanks. So thanks to all of you, the speakers, authors, and attendees for being with us for these 2 days. Without you, we will not be able to make these 2 wonderful days. And huge thanks to our keynote speakers, Simon Peter Jones and Richard Eisenberg. I think the keynotes were very well attended. The room were very packed. And I hear people talking about these talks in the hallway. So I'm sure it's very well received. And great thanks also to the co-chair. So we have two chairs. So Garrick was the senior chair and I'm the junior chair. And Garrick's duty is to receive and reply to dozens of my emails and help me out in the difficult situations. So I won't be able to make it without him. So thanks, Garrett, who unfortunately cannot make it to ICFP this year. And also thanks the Haskell Steering Committee, who guided us through this whole process, and the ICFP SPLASH organizers and the volunteers. And if you see the volunteers passing mics around, huge thanks to them for helping organize the sessions. And also we have a wonderful program committee who did all the work for reviewing the papers and the talk proposals. I think each of them did like 3-4 papers and a few talk proposal reviewing, so it's a lot of work. And they provided very constructive and helpful review, so thanks to the program committee as well. And a few words about the submission processes. So we have the usual paper categories. It's the same as last year. We have research papers, or what we call regular papers. And we have functional pearls, and we have tutorials, experience reports, and demo proposals. And all those submissions, they go through a lightweight double-blind reviewing. That means when they submit the paper and when the reviewers review the paper, they will not know who the authors are. But afterwards, for the discussion phase, the author identity will be reviewed just to help reviewers put the work into context. And this year, we have received 19 submissions in total for all the categories. We received 4 functional pearls, 1 experience report, 2 demos, and 12 regular papers. And we ensure that each submission receives at least 3 reviews. And in the end, we accepted 9 submissions, including 2 pearls and 1 experience report and 6 regular papers. So if you take all the categories into consideration, we have roughly 47.4 acceptance rate. So that thing was, similar to last year. Okay. To add on that, I think pre-pandemic, the number of submissions were around 60-ish, and after pandemic, we have dropped down to 20, but we seem to have stabilized a little bit again around 20. I don't know where the other 10 submissions have gone, but please encourage people to submit to Haskell Symposium. And you may have noticed something new this year. The first is, I think somebody mentioned that during Richard's keynote as well, which is we don't have Haskell implementers workshop this year at ICFP. And that's not because HIW is gone, but it's because we moved HIW to be co-located with ZuriHack. There's a bunch of Haskell designers, users, hackers, implementers at ZuriHack already who are not necessarily interested in the academic aspects of Haskell. So we thought it might make sense to have that be co-located with ZuriHack. And from what I have heard, it was a huge success. So I think we are going to do that again next year, unless there are significant changes we have to make. And another new thing that happened this year is we have, in addition to the Code for Papers track, we have a separate Code for Talks track. For this is partly because we don't have HIW anymore at ICFP, but for people who want to share their work around Haskell, they can submit a talk proposal. And many other workshops do this as well, like OCaml and Tidy. They accept work in progress to be presented as the talk, and those talks are not included in the proceedings. And for this year, we just required talk proposals to be, next one. Yes, talk proposals to be, we just require an abstract with no more than 300 words. This is the same requirement as HIW. So we sort of try to see how those talk proposals work and decide whether we'll keep it. Admittedly, I think 300 words are not sort of enough to actually imagine how the talk will go. So as for some talks, I think they submitted PDFs as well, like talk slides, or like maybe a PDF for work in progress to help the reviewers contextualize the work a little bit. And the other way we could do it next year maybe is to require a 2-page of extended abstract, so it includes more details about what would be included in the talk. And for this track, we also made the deadline very close to the conference, with the idea being, like, if you know that you are going to attend SFP, maybe you would consider giving a talk at the Haskell Symposium to share your work in progress. So that's also why we made the deadline very close to the conference. But then later I also realized maybe some people would like to know for sure if they are going to talk about anything at the conference beforehand. So maybe there is something we can do about that as well next year. Yes, we together we received 6 talk proposals, and we decided to accept all of them. And the problem that causes is in the end, we could not fit everything into the schedule. So for the research papers, we have a 30 minutes talk for them that has been decided beforehand, and then to fit all the talks into the schedule, in the end, we can only make them 20 minutes. So I also heard because this is a new track this year, like many people have not heard about this, the Code for Talks track for Haskell Symposium. I heard people saying that if they had known there was such a track, they would submit something. So please spread the words that we are going to have this new track, and maybe we are going to keep this new track for next year. So please encourage people to submit talk proposals and talk at the Haskell Symposium. And I have a few thoughts going through this whole process, and I think maybe some changes we could make for next year. The first is, if you still remember, for the Code for Papers track, we still accept demos, but then separately we have this Code for Talks proposal. And maybe something we can do next year is to actually merge these two things, because the demo is a talk, right? And you could also do that with 300 words of abstract or extended 2-page extended abstract. And the format and the deadline for the talk proposals. So this year we also invited authors of rejected papers to give a talk. I think some of them did that and some of them didn't. And I think an easier process to make that happen might be just we provide additional checkbooks. If your paper got unfortunately rejected, would you still be willing to present a talk? Then we can still accept those submissions as talks. And there's some question about the artifact, I think, of the papers. I think that's something maybe we should do better. I think it's possible to at least make an artifact available badge for the papers, so they can put their artifact in the ACM digital library. So we have a persistent link for those implementations and artifacts, so that people in the future can still know where to find them, right? And the last thing is next year's chair. So next year we will have Lindsay Cooper as our chair. I think she unfortunately could not make it to the talk, but she is around. So if you have any feedback about the Haskell Symposium, anything you think we could do better for next year, please feel free to let me or her know. We will be around at the conference. And that's everything I have to say. So I hope to see many of you next year at ICFP 2026. Thank you. Yeah, then, yes.
It's just that I know that I don't know whether Lindsay is here and whether I'll catch her or not. But there should be some kind of peer review, especially since that small people know about